Alrighty, hi everyone. Welcome to the complete Rust bootcamp. Wouldn't call it complete. This is probably part one. There's like a lot of things to do in Rust, but this covers a decent chunk of what you need to create your first set of applications, not just, solving data structures algorithms questions, but also creating, let's say, a simple HTTP server, a simple backend for your full stack application. Let me preface with some phrases and take you through a bunch of gotchas and disclaimers before you get into anything. Rust is hard and very hard even for very senior people. It probably takes years for you to become extremely comfortable in it. I think the same is true for languages like C or Zig. So take your time and pick and choose whether or not you want to learn it. Even though we're learning it in a very beginner friendly fashion here, there is a high probability that when you hit a production system or try to code a production system, you don't understand things there because it's highly verbose the way you have to write code in Rust compared to how you've been writing it in JavaScript or Python. Why would you want to learn Rust if it's just easier to write code in Python or JavaScript? One, if you have to write languages where you need very low level access to your system, when you have to write languages where you need extremely low latency, if you want to write smart contracts on the Solana blockchain, you sort of have to use Rust. There is no other option, or some other low level language like C. So either way, there are cases where you can't really skip it, but for most use cases, a simple language like JavaScript or TypeScript works, especially for, full stack applications or backends of them. So, pick and choose whether or not you want to do it. A few phrases before we start. These are like people who know Rust should be fairly easy to understand these. People who don't know Rust, you will eventually come back to these and understand them. The first one is, in Rust, if your program compiles, it probably works. It basically means it's very hard to make your program compile. There are a lot of errors that you have to go through. You have to code a certain way. And, if you try to write bad code or code in a way that chalo koi nahi, this might just work, the compiler will throw a lot of errors at you. And a lot of times, if your code compiled, most probably it's doing the thing it was supposed to do. You don't have to do a bunch of runtime checks and go to the browser and test the thing. So that's one of the benefits of having very strict checks during compilations. Number two, you can't segfault if you don't have a null. This is not just true for Rust. A lot of languages don't have nulls, but have other ways of handling none values. Same is true for Rust. So there is a negligible probability you get a segfault in Rust because of the way it's written, especially when it comes to trying to access null values, which is fairly common in C or C++. Lastly, Rust does not hide the complexity from developers, but it offers the right tools to manage all the complexity. So I'm repeating again, it's very complex code that you write from time to time. A lot of times, jarring you. If you've moved from JavaScript to TypeScript, you might have seen this transition once, especially if you're writing very core TypeScript. So similar transition you might see here, but as you see the same code again and again 100 times, 111th time, you'll probably be, good to kind of understand what's happening there. That's a brief bunch of disclaimers. Pick and choose whether or not you want to do it. But if you are aiming for becoming a Web3 developer, and if you are thinking of joining the Web3 cohort, I would consider this to be a very nice, I wouldn't call it a prerequisite because we will cover all of these again in the cohort, but still a very nice resource to look at even during the cohort or otherwise to get the basics of Rust, maybe a little more advanced concepts out of the way as well. With that, what are the basic concepts and advanced concepts we're learning? What is the syllabus for this specific video? I've divided it into two parts. The easy and the hard. This can be easy based on your level. If you already know another language, this should be fairly straightforward. If this is the first time you're programming, then I wouldn't call this like very easy. But yeah, I'm assuming if you're thinking of diving directly into code, into Rust, you've probably coded a bit. So the things that are easy is how do you install Rust onto your machine? How do you set up your IDE to make sure you see all the right colors? You're able to navigate from one file to another. You're able to compile your code. In initializing a project locally, throughout this tutorial, you don't need to run Rust locally. You can actually use Replit and it'll just work. We're not doing anything too complex. Even if you're doing complex things, I think Replit is like pretty like it can handle complex projects with a bunch of modules as well. But today, most probably you're restricted to one file until we reach towards the end. So you should be fine if you use a REPL. What is REPL? What is Replit? It's this website that lets you create playgrounds to write Rust code. So you can do it directly in your browser and you don't have to bring it locally and run it on your machine. So pick and choose if you want to use Replit or if you want to do it locally. I would just do it locally in case you've already installed other things. If you've installed Node.js, fairly easy to install. Then we'll understand variables, numbers, strings, booleans. How can you create simple primitives in Rust? We'll not be covering arrays and objects just yet. We'll come to them later on. But initially we'll be covering. Ideally, we should just cover numbers and bools because strings are a little weird in Rust, but we'll try to cover basics of strings, and then we'll eventually come to some advanced concepts in strings as well. Conditionals, if-else statements, loops, for loops, while loops, fairly simple, straightforward stuff. Creating a function. Up until this point should be very easy. After this, we'll understand a bunch of other things. So we'll move to basically the hard stuff and come back here. But when we come back here, structs should not be too difficult, especially if you've done structs in C++. Enums are again fairly common. You might have seen them in TypeScript, pretty much do the same thing here. Optional and result, two pretty commonly used enums that Rust provides you. Pattern matching if you're using one of these. And then lastly, something called package management, basically bringing in other people's modules into your own module. If you've heard of NPM and how you can install Express into your Node.js project and use it, similarly, Rust provides you the same thing. How can you use the very sort of pretty advanced libraries, modules that people have already written and use their code and not write everything from scratch. Now, as I said, we'll be doing some of this, then we'll move to some hard stuff and then we'll come back here. What is the hard stuff? This is what makes Rust. Like this is what sort of, the maintainers, whoever started Rust sort of thought of as the mental model. And why is it so memory safe? Why is it so fast? It's because of these things that have been mentioned here. These take a lot of iterations for you to understand. You might not understand, for example, the last three: ownership, borrowing, and references the first time, which is fine. And all of these will probably take you more than 10 iterations to, go through again and again, write a lot of code in them, and then eventually understand. But to just, brief out what we're doing, memory management, this one should be straightforward. Just understanding how does Rust do memory management? How is it different from JavaScript? How is it different from C? And what conscious choices the maintainers took to write Rust in this specific way. Then we'll understand mutability, which is, it's not just a Rust concept, but Rust enforces mutability extremely hard. So what does mutability mean? Then understanding stack versus heap. You might have heard of this in C. Ownership, which is a Rust specific concept. Borrowing, Rust specific. References, the way we'll be learning it again, Rust specific. So all last three of them are highly Rust specific, which means you've probably never heard of them before if you're in this tutorial, or, never seen what they mean. So here is where, I'll see a lot of drop off. I'm assuming, a lot of people will not understand, which is fine. I did not understand any of these for a while. This was how I was coding. I directly jumped into a code base and, eventually when I ran into a bunch of compile time errors is when I had to understand ownership and borrowing, things like these. So you can always come back to these, but, if you are on this video, try to go through this section again and again to, as I said, the first three you should be able to understand, but the next three should be, a little dilly-dally. So pick and choose. Lastly, after we have gone through all of these, I think this is enough for a single video because number one, I'm on a clock. I have a flight to catch. I don't think I'll be able to cover everything. And number two, I think this is enough for a single video. This also covers a lot of the basics plus something extra. So, you should be fine for most use cases. But yeah, some traits is something you should definitely know. Generics is not too difficult and you probably know them if you've already done TypeScript. Lifetimes is also sort of important, especially if you're writing Web3 contracts in Solana eventually. Multi-threading, not really important. It is important, but it's fairly easy to understand. Macros, very hard to understand. Feel free to skip. And then, futures and async await, which is, again, not too difficult to understand, especially if you're using, async await. So that's a brief. That's what we're learning. Again, fairly easy stuff. Easy, but moderately hard. 4, 5, 6 are going to be moderately hard. Very hard. Okay-ish, very hard, okay-ish, very hard, and okay-ish. That's a brief. With that, I think we have enough context of the high-level syllabus. Let's kick things off. Let's start with the first module. Again, just to show the structure of the code, the syllabus. We'll first go through the basics from here to here. Then there will be the jargons that we need to understand, the Rust-specific memory management concepts. This section, in case you don't understand, feel free to skip / Even if you understand partially, it's fine. You can move on to the last section from structs over to package management. And lastly, we have some leftovers. I'll leave some resources. There is a very high probability there's a video number 2 in this specific bootcamp / series where we'll try to cover all of these and a few project ideas, which you have enough knowledge by this point to write at least a basic version of those ideas. Enough context, let's get right into it. Let's understand the first slide. Why Rust and why isn't Node.js enough? Why would you want to make this transition? Why would you even want to think of learning Rust? Why would you want to use Rust over Node.js or Python, let's say? And there are like standard reasons why these languages are different. Let's go over them one by one. Generally, it's recommended to use Node.js or Python as your first language because they're easier to write. Why are they easier to write? Because they don't have something called type safety. They don't enforce types anywhere. If you look over here, I've written let x equal to 1, where x is a number, and then I've tried to change it to be a string. And there are no errors that are thrown. If I try to write the same code in my console right now, it throws no error. I see no red errors over here, which tells me JavaScript doesn't care about types. You can assign a variable to be a number and then change it to be a string in the very next line. That's not great. The reason for this is, you should have strict types. Most probably there is some bug in the code that you've written if you have to do type conversions. Or at the very least, you should explicitly tell x can be a number also and x can be a string also. JavaScript doesn't let you do this. Rust enforces this. There is no way for you to get around this. In case you're defining a variable, you have to define its type. Here, if I've written let x equal to 1, this is very simple Rust code, 3-line code, basically initializes a variable and tries to change the value in there to be a string. If you try to do the same thing here, you will see an error. Let's quickly try that out in Replit. Also might be a good time for you to write some code. If I type let x equal to 1 and then try to update the value to be a string, you will see I see a red squiggly over here. If I give it a second, there you go. And it says mismatched types, expected integer, found string. Rust is not allowing you to provide or change the type of a variable. C++ does the exact same thing. If you open a C++ REPL and try to write a similar code defining a number and then changing to be a string, it will not work. It will give you a compilation error. What does compilation error mean? It means even before running it, it is telling me, bro, there is an error over here. You should fix it. JavaScript does not enforce this. As you can see over here, Rust does enforce this. But JavaScript folks realized this is a problem and introduced TypeScript. So this isn't really a problem anymore. If you are using TypeScript, then you should be fine. You have very strict types everywhere. Same is true for Python as well. Python also has. You can introduce types in Python today as well. All right. The second reason you might want to use Rust is that it's a systems language. Now this means different things for different people. What it generally means is you have access to a lot of resources on the machine that you're running Rust on or even C on, versus if you're running JavaScript, you will not have access to these resources on the machine. What are these resources? Some common ones include, for example, how many of you have heard of RAM or memory, random access memory, which is pretty much the place where your program is running and holding all of its variables. If you write a Rust process, you get access to this memory in a weird way, like not exactly C, you really get access to the memory. Rust, you can get access to the memory, which means you can put variables here, remove variables from here, have references, things like these. That is what a low level language means. It runs very close to your machine. And if you ever want to build things like a compiler, something that's closer to your operating system, something that wants to access your file system and memory for whatever reason, you cannot do it in a language like JavaScript, but you can do it in a language like Rust. The other reason is, Rust is incredibly fast compared to JavaScript. So even if you can build a use case in JS, let's say you're trying to build a very weird use case. One decent example here is if you're trying to build a WebRTC server. Even though you can build it in JavaScript, what is a WebRTC server? Pretty much, running WebRTC on the backend. WebRTC is a protocol. If you don't know it, that's fine. But if you're trying to build a project that lets you create the WebRTC protocol on the backend, you will most probably not write it in JavaScript, but write in a faster language like Rust, C, Golang. Prime examples of this are MediaSoup, which is a WebRTC backend that's written in C and Rust, and Python, which is written in Golang. There is a project called, WebRTC JS or something like that, but it's not as widely used as these two. And the reason is because these are comparatively much faster. In fact, MediaSoup goes one step ahead, and it is actually written, it provides a high-level JavaScript API, which basically means whenever you're writing code using MediaSoup, you actually do a npm install MediaSoup and you bring a JavaScript library locally. You actually do import some MediaSoup construct from MediaSoup in a JavaScript file, and then do whatever it is, MediaSoup dot create WebRTC connection. So it's actually written in JavaScript, but the JavaScript is just a high-level API to talk to a C worker or a Rust worker. So a lot of times projects will expose a high-level API in JavaScript just because it's a popularly used language, just because people writing code in Node.js. But under the hood, the JavaScript API just calls a C++, a C process, or a Rust process, because these are much faster for use cases like these, WebRTC being a prime example for it. So these are the two other reasons why you might want to use Rust. It's faster if you're building a trading application, if you're building an exchange. Zig, Golang, C, Rust are the popularly used languages. Would be pretty stupid for you to use Node.js on a backend where latency matters so much. If you're creating a trading bot that if is creating a lot of orders, trades, and monitoring a bunch of exchanges, you want all of the requests that are going from your whatever trading server, wherever it is, to Binance or wherever you're sending requests to place orders and delete them, to be really fast. You want your server that's trying to guess what the current price of X is, or is trying to aggregate the price of a stock, let's say Google stock, from 10 different places, to be really fast and spit out the current value so that you can place these orders. So whenever you see a trading server, TS doesn't stand for TypeScript, it stands for trading server. It will be written in Golang, Zig, Rust, C, and that is why companies, trading firms sort of prefer, or I guess Jane Street prefers OCaml, but you get the idea. These languages are much faster, both in terms of like how they run, in the sense, if you write a for loop both the places, you will see the for loop in Rust will run much faster than in JavaScript, but also because Rust has a separate compilation steps. Actually, all of these languages do, most of them. So when you have a separate compilation step, which means if this is the Rust code that you've written, you first build it into a binary and then just run the binary. All of your compilation happens first upfront, and then this is your final code that's running really fast. There are a lot of checks that you can do, which is also called static analysis in Rust. You're statically analyzing the code. You're not actually running the code. You're analyzing it and making sure, bro, is everything safe? Has this person written the right code? And if they have, you're converting it into a binary, and then the binary is finally running. Versus in JavaScript or in Python, it runs line by line. It's compiling and running at the same time. It's not able to do a bunch of optimizations that the Rust compiler does when you spit out a binary from the original Rust code. So these are another two reasons why Rust is generally faster, or most compilation languages, or most languages that are compiled down to a binary, will do a bunch of optimizations, and the final binary that comes out will be much faster compared to a language that's interpreting it, compiling it, and running it line by line, which is something that JavaScript does. Lastly, concurrency. This isn't Rust specific. Java lets you do concurrency. Golang lets you do concurrency. What does concurrency mean? Running multiple threads on a single machine. So if this is your Mac machine, which has 32 cores, if you're running a JavaScript process here, if you ever run node index.js, it will only run on a single core of this machine, which means there is no point of you to have such a beefy machine. Even if you have a machine that's 32 core, 64 core, doesn't matter how big it is, unless you've done a bunch of weird things, and not weird things, like very standard things in Node.js to make it multi-core, your Node.js code will only run on one of these 32 cores. Rest of them will be idle. Versus if you're using Java, if you're using Rust, it lets you spawn what are called threads. So, if you run cargo run, which is the way you run or compile and run a Rust project locally, you can spawn multiple threads from it, and each thread can independently run on one of these cores. What are cores, Harkirat? If you've ever opened system preferences or, about this Mac and gone through about this system, let's see where it is. There you go. It says 10 core CPU with 8 performance cores and 2 efficiency cores, which means my specific machine has 10 cores. Whenever you're buying a machine, you sort of ask how many cores this machine has, right? Since my machine has 10 cores, if I'm running a Node.js process locally, it can only access one of those 10 cores because Node.js is what's called single threaded. But Rust or Java or Go let you spawn something called threads, which is, a very OS concept if you've gone through your operating system class, which can run on multiple cores. So in my Rust process can pretty much use the complete power of my machine. My Node.js process cannot. Are there ways to make the Node.js process run on 10 cores? Yes, but it's non-standard. You have to go one step beyond to make that happen, versus you can just do it like this in Rust. And each of these threads can also share resources. You cannot do that or that's sort of hard to do in Node.js. You have to do something called IPC or inter-process communication, just a buzzword to read about later on. So if you want to do shared multiple threads in Node.js, you have to use IPC, which is sort of slow, versus if you're using C, Rust, then it's easy for you to access shared resources in multiple threads and share data much faster than Node.js. Cool. That's concurrency. Nothing specific to Rust. Happens in a lot of languages. And lastly, memory safe. Here is where, C and Rust are different. C has its own way to do memory management. If you've heard of malloc, and I keep forgetting if it's calloc or alloc, but you can manually allocate and deallocate resources on memory or variables on memory. You can have access to memory and reference variables there, and you can dereference them. You cannot do that in Rust. You can do something else in Rust, which makes it memory safe, or like maybe you can do it in Rust. My point is, it's very different how you do memory safety in Rust, in C, and in JavaScript. Let's discuss all of these three, I think, in the next slide. Let's see. Initializing Rust locally. No, we'll be getting to some of this when we reach memory management in Rust. Yeah. So feel free to ignore this point for now. Memory, why is it memory safe? How is memory safety different in Rust? This is sort of an important concept, but as I said, it'll come later. But memory management / memory safety. How is it different in Rust, C, and JavaScript is something we'll be discussing when we reach this specific slide called memory management. Until then, let's write some code. But this is a super important reason why you might want to use Rust, not just over JavaScript, but also over a language like C. This is where, if you have a choice between two fast languages that are used for trading, you might want to go for Rust because it's significantly more memory safe. There are much less, there's a very low probability for you to do a dangling pointer error, a null pointer exception, or null pointer error, whatever that's called in C, versus doing it in a language like C. Let's get to that later though. Next up, let's move on to initializing a Rust project locally, which you can totally skip if you're using something like Replit. But if you're not using Replit and would like to install Rust locally, this slide is for you. All right, installing Rust locally, fairly simple steps in this slide. We'll understand how can you bring the Rust compiler locally to your machine. If you're lazy and if you want to code on Replit, that's fine as well. There's no downside here. But generally would urge you to, start to bring code locally as soon as possible, because you can customize your IDE, add some standard behaviors. It'll be useful if you're building an HTTP app, so you can start your database locally, things like these. So never a bad idea to start it locally. If you're a complete beginner, then feel free to use Replit. Rust projects can be used for a lot of things. That includes creating backends for your full stack application, creating command line interfaces, creating browsers. Believe it or not, Rust was introduced at the Mozilla Foundation because they wanted to make Firefox much faster, and eventually they moved the complete browser over to Rust or the browser engine, one of these two things. And what's that project called? I totally forgot. But that was the initialization of Rust, like why Rust was sort of introduced. And lastly, I've written great code editors here because I don't know if you've heard of Zed, which is, popularly coming up as the next text editor that's being written purely in Rust. For this bootcamp, we'll be getting comfortable with the syntax of Rust, which means we probably are not creating any of these. We might get a flavor of building a full stack application by the end of it. But yeah, mostly just writing simple code like you would on a lead code prompt, I guess. For the most part of the video, a Replit playground is good enough. But if you want to bring it locally, then the steps are over here, depending on the operating system you're on. Seems like if you're, it'll pretty much give you the steps based on your OS. It knows that I'm likely on Mac OS, which is why these are the steps that it gave me. If I copy this over and go to a terminal and paste it, what was I installing here? Paste it. It should install Rust for me locally. I already have it, which is why I'm not going to redo it, but feel free to like go through the steps basically if you don't have Rust installed locally. I'm not doing an OS specific installation, but pretty much you should see a script here that you can copy and paste in your terminal. If that does not work, Rust has something called Rust Up, pretty much like a version manager, very similar to NVM, that lets you sort of, install Rust using a version manager, upgrade, downgrade, so on and so forth. Feel free to pick whatever method you want. I'm going to use the first one. I actually already have done the first one. So all I have to do to confirm whether or not it works for me is run the command cargo. If you've done JavaScript before, cargo is very similar to npm. It's a package manager and lets you sort of run, build packages locally. So the best way to know if you have Rust and the Rust compiler locally is to run the cargo command. If it spits out an output like this, it means you're good to go. If it spits out an output that looks something like this, that the command is not found, it means you've messed up the installation and you sort of have to go through the steps again. A lot of times you might have installed it in the wrong place or incorrectly. So feel free to try sudo cargo. But generally, aim for cargo. If cargo as a command runs for you, it means you're good to go. If not, then you have to, fix the installation locally, which, you will have to choose some class. If it takes a really long time, feel free to ignore for now and go to Replit for all the code that we'll be writing today. That's all for this slide. Let's move on to the next one. That lets you initialize a project locally. We have installed Rust locally. We haven't yet initialized a project, which means, have a simple main.rs file locally. Again, this is something you can ignore if you're using Replit, but if you're not using Replit, the way to initialize a Rust project locally is by running the cargo init command. The commands above it are just to create a folder and then change the directory to that folder. And then if you run the command cargo init, it will initialize a simple main.rs file and a cargo.toml file for you. So two files you will see when you initialize a project, a cargo.toml file and a main.rs file. If you come from the Node.js world, the main.rs file is similar to an index.js file, your entry point file basically. And the cargo.toml file is similar to a package.json where you can describe all the external packages you are using. In case you're not from the Node.js world, feel free to ignore package.json, index.js. Just make sure you have these two files locally as soon as you run the cargo init command. So let's do that next. Let's open the terminal. Let's go to my projects /100x folder. Let's create a new folder here called Rust proj. Let's go to the Rust proj folder and run cargo init. And once you do, it'll spit out something like this. It says created binary application package. There are a bunch of things you can do with the Rust. Creating an end user application is one, but you can also create something called a library that other people can use. When you run cargo init, it initializes an end user app. What is an end user app? A full stack application ka backend that you might be running. A command line interface that might finally run on a terminal very similar to this one. These are end user applications. What are libraries? The other thing that you can initialize if you run the command cargo init --lib, I think. Let's just confirm the command here. Yeah, cargo init --lib. It'll initialize a library, which means you cannot independently run it. Other projects can use your library and run it, but we're not focused on libraries for this specific package or for this specific bootcamp. So feel free to run cargo init and open the folder that you're currently in Visual Studio Code. Or I guess whatever your ID of choice is. Once you do, you will see there is a source/main.rs file, which has code very similar to what we saw on Replit, which is function main print hello world, and then a cargo.toml file, which, as I said, is very similar to a package.json file. It gives a name to your package, the current version, the edition of the Rust compiler you're using, and all the external packages that you have. We have 0 external packages right now. We will be adding some towards the end of the video. So that's pretty much empty, and that's all that we have to do for, that's all that we have to touch in cargo.toml for a really long time. We will be focused on main.rs. You might not see a run button here, a debug button here, in case you're using Visual Studio Code. So another good thing to do here is go through the next step, which is the VS Code setup plus, running the Hello World project locally. So if you are using Visual Studio Code, you can bring in an extension called the Rust Analyzer. So if you go to the extensions section here and search for Rust, it'll give you a bunch of these extensions that you can bring in. But the one that we're interested in today is the Rust Analyzer. If you install this, which as you can see, I already have it installed, you should see the run, the main, the debug function buttons here. You can actually hover over something and click on it and reach the actual definition. So this is pretty much something you need if you want to have a usable Visual Studio Code setup. And this is the only one that's really needed. You can actually add a few others. For example, there are some extra extensions that I've written here. One of them is code LLDB. One of them is a simple toml parser. If you looked at the cargo.toml file, it's all white. It doesn't have the right colors. So you can get a toml parser extension. I'm sure there are many. And if you try to click on debug, it will most probably not run for you. What is debugging? Pretty much lets you, put breakpoints in various places and debug your application. So if you want to debug your application, you will need to bring another project locally or another extension locally called code LLDB. That'll pretty much let you do debugging locally. Let me fix that really quickly. All right. Now, if I try to create a breakpoint and click on debug, you will see the code sort of gets stuck at a point, and I can debug from this point onwards. So if you want local debugging, which frankly you should install code LLDB. If you just want very basic Rust file to file, going to a definition, things like these, then just the Rust Analyzer is good enough. That's all you need for a basic setup. Once you're able to set up the project locally, the way to see if things are working correctly is, one, you can always click on the run button, and if it prints out hello world, it means you're good to go. You have the same things as we did on Replit over here. If I print hello world here and click on run, what do I see on the right? I see building, but once it's built, I see hello world. The same thing I see in the Visual Studio Code terminal over here. If I run, if I click the run button here, or you can run cargo run in the folder that you're at, and that will pretty much run your project. And you see hello world over here. You see hello world over here. So clicking on the button here is the same as running cargo run over here. That's probably what they're running over here as well. A good question to have at this point is, Harkirat, you to said that Rust has two steps, one build step and one actual step to run. If you remember a while back, I said most compiled languages, including Rust, will have two steps to run a project. First, you will build it, optimize it, and then you will run your final application. But Harkirat, here to you're only running it, you're not having two separate steps, one to build and one to run. And the answer is that is because when you click on run, it pretty much does both of the things. If you want to independently build and independently run, you can do that as well. As you can see, it says over here, finished dev. Pretty much this is the step that's building the project, and this is the project step that's actually running it. So if you go to /target/debug/rust-proj, this is your final binary that got spit out from this original code. If I click enter here, you see hello world. And if I run cargo build is when this binary is created. If I delete the target folder over here and then rerun cargo build, you will see the target/debug folder is created again. If I run /rust proj over here, you will see hello world. So we do have a step of compilation. You just don't see it when you click on the run button, or if you run cargo run over here. Harkirat, what is debug? Why is it called debug? What does debug over here mean? It means you're running it in dev mode. You're trying it out locally. This isn't your release build. What is a release build? A build that actually goes to your AWS server and gets deployed. When you're running cargo build locally, unless you give it a -- release argument, it will not create an optimized build. But if you do give it one, then it will create something in the target/release folder, which is a more optimized version of the library binary, but you don't need a more optimized version when you're trying it out locally. So long story short, what is the way to run a Rust project locally? Step number 1, install cargo or install Rust locally. Step number 2, cargo init to actually initialize a project in a folder. How do you know that the project has been initialized? My new keyboard is killing me here. How do you know that the project has been initialized? If you see main.rs and cargo.toml, means you're good to go. Open it in Visual Studio Code, add 2 extensions over here, code LLDB and the Rust analyzer, and then change your code to whatever you want. Let's say, hello one, and then run cargo run to actually run the project, and you're good to go. Cool. That is how you bring it locally. Harkirat, it was too complicated. In case it was, feel free to use replit throughout. The steps remain the same. Just make sure you're writing code here rather than writing it locally, but would generally urge you to bring it locally if it's not too difficult. So yeah, I would urge you to bring the code locally and run it locally. With that, let's get into writing some more code. What's the next slide here? The next slide is on basic variables in Rust. So we're slowly going to write code now. I'm glad you've reached this point. I think this is enough theory to discuss. And now let's write some code before we move to some advanced concepts like memory management in Rust. Understanding simple variables in Rust. This section should be simple, even though I've added some complexity from time to time, specifically in the strings part. We don't have to get very deep into this. I am for this video, but feel free to skip some parts because usually you use numbers, strings, and booleans fairly simply in a Rust project. Strings create some complexity from time to time, but we'll not get too much into the complexity of strings just yet. Before we write any more code, let's quickly discuss the variables that we can understand and some Rust concepts before we get into the meat of the code. You can define a variable by using let, very similar to JavaScript, and you can assign the type of the variable, or it can also be inferred. What does that mean? Okay, let's say you're creating a number. This is some fairly simple code of a function, the main function, where you define a variable called x. And if you look at it, the type of this is I32. This is something new. This is something weird if you might not have seen, especially if you come from, the JavaScript world, because in the JavaScript world, if you ever define a variable, it looks something like this. Let num:_number equal to 1 to 3. Never have you seen something like I32 over here. So what is I32 and what does it represent? If you've gone through C, C++, this is fairly straightforward to you. Numbers can be of various sizes. You might need a very small number from time to time. Let's say, 100. You might need a very big number from time to time. So Rust lets you describe what is the size of this number. Is it a 8-bit number? Is it a 16-bit number, 32-bit, 64-bit, 128-bit? That's what the number over here means. What does I over here mean? It means that it is a signed integer. It is not a unsigned integer. What is the difference between signed and unsigned? Computer science class, if you have gone through it. If not, I'm going to explain you a little bit of what this means. There are usually 2 types of integers that you store in a language like C or Rust. They're either unsigned integers or signed integers. First of all, before we proceed at all, why do you even need this, Harkirat? Why can I not just use numbers like I use in JavaScript? And the answer is, what is Rust? It's a memory safe language that aims to have the smallest memory footprint. So it would want, if you know you are only going to use a very small number, let's say that will have values from 1 to 10. Why do you want to reserve 128 bits in memory? What does in memory mean? It means in the end, what is a program? What is a C++ program? Where is it running? it is running in the RAM of your machine, right? If this is your Mac machine, your Mac machine has the random access memory here. Could be 1 GB, could be 32 GB based on how beefy of a machine you have. And whenever you define a variable, whenever you define a I8 variable, I16, I32 variable, you're asking for some number of bits over here. Here I need 8 bits in this case from inside the RAM. I need 16 bits, so on and so forth. So if you know something is really small, you would want to ask for only 8 bits. Here, my number can fit in 8 bits. Even if I get a 128-bit number, most initial bits will be 0, and then the last one will be zeros and ones. So why not just get a small space in memory? What does I8 mean? It means a very small space here. What does I128 mean? It means taking up a lot of space here because I have a very big number. So you can describe how big of a number you need. If I'm in a Rust program, if I'm defining a variable, that's a number, let x equal to 5. By default, this is I32, which means it will reserve 32 bits in memory. But if I know it's a small number, I can make it I8. Here I only need 8 bits. This is a very small number called 5. I don't need to reserve 32 bits in memory for such a small variable. Harkirat, how big a number can I store here? Well, it's 8 bits. What can a bit be? A bit can either be 0 or be 1, which means there are 2 possibilities here, 2 possibilities here, 2 possibilities here, 2 possibilities here, so on and so forth. By simple permutation and combination, the number ideally should be 2 to the power 8. How do you do power here? 2 to the power 8 should be the number of, like the biggest number I can store here. If I want to store, 32 here, I can. It'll be a 1 0 0 0 0, something like that. If I want to store a 33 over here, it'll look something like this: 1 over here, and then 0 over here, 0 over here, 0 over here, and 1 over here. If you understand binary, this is straightforward. If you don't understand binary, feel free to ignore as well. You don't really need this. I'm going too much into the depths of numbers. But yeah, what is the maximum number you can store in I8? It's not 2 raised to the power 8. It's actually 2 raised to the power 7, because the very first bit is reserved for the sign of the number. I can have a minus 32 stored in here as well, right? Or I can have a plus 32 stored here as well. So where would the value, whether is it a positive number or negative number, be stored? And it's usually stored in the last bit over here, which means the maximum positive number that I can store here is 2 to the power 7, and the least number is actually 2 raised to the power minus 2 raised to the power 7. The maximum number is actually not 2 raised to the power 7, it's 2 raised to the power 7 minus 1, because you also have to store 0. So this is the usual range of numbers. If you know your number is going to be between minus 2 raised to the power 7, which I think is minus 127, to plus 126, minus 128 to 127, I think that's right. If you know your number range is going to be this, you will choose an I8. If you think it will be, whatever, 2 raised to the power 15 to minus 2 raised to the power 15 to 2 raised to the power 15 minus 1, then you'll choose I16, so on and so forth. By default, you get I32. If you don't understand any of this, it is fine. You can simply do a let x equal to 5, and by default, it will be a 32-bit integer, and it will have a sign. If you know your number is going to be positive always, then you can actually move all of these bits here, and you can have a slightly bigger number. If you know the first bit can be used as a 0 and 1 as well, and you don't need a sign, it's positive by default, then the number that you can get to here is 2 raised to the power 8 minus 1. That's a brief about unsigned and signed integers. If you don't understand, ignore. You don't need to understand a lot of this. You can totally just be like, okay, if I want to define a number, it'll look something like this. If I want to define an unsigned number, which means if I know for a fact it will be positive, I will do this. The first one can be negative, the second one cannot be negative. If I try to make it negative, the compiler complains. An unsigned number or integer needs to be positive. A signed number can be negative and positive as well. It's still complaining. What does it say? Cannot apply unity operator minus to it. Okay, there you go. And lastly, if you want a float, which means a decimal point integer, basically, you can pretty much do something like this: f32 and 0.001, let's say. So that's how you do numbers. Number that can be both positive and negative, number that can be just positive, number that can be both positive and negative, and also can have decimal places afterwards. If I try to print all 3 of these, I can do that by doing Yeah, something like this. X is going to be the value, that's the first argument over here. Y is going to be the value, that's the second argument over here. Z is going to be the value, that's the third argument here. If this feels jarring, you can just do this. Okay, yeah, this is what X is. Print X is this variable right here, the first argument, and then you can print Y, and then you can print Z. Feel free to choose. If this feels straightforward or simpler, then this is fine. If you try to run this, you will see what gets printed with a bunch of warnings. -5 gets printed, which is the value of X. Similarly, if I try to print Y, along with a bunch of warnings, which feel free to ignore for now, 1000 gets printed if I print Z. Along with a bunch of warnings, you will see 1000.001 got printed, which is the third number over here. So to quickly recap, how do you do numbers in Rust? You don't have to give it any type. By default, it will infer a type. If you're using decimal places, then it will infer the type as F64. That's a 64-bit floating point number. If you don't give it a type here, irrespective of whether it's a positive or negative integer, it will by default infer the type I32, and same thing over here. If you know your number is really small, if it's going to lie between -128 to 127, then you can simply do something like I8 over here, and you're still good to go. As long as this number isn't very big, that cannot fit in an 8-bit integer, you'll be fine. If you do make this number really big, then of course the Rust compiler will complain. What does it say? It says literal out of range for I8. This number does not fit in I8, where the range is -128 to 127. So if you are using I8, you need to make sure the number is really small. That's a brief about numbers. Even if you just understand this much, you're fine. If you want to solve any algorithmic problem on lead code, this much is good enough. You don't even have to write the type. It can be inferred automatically. Usually you use 32-bit integers in programming, unless you have a very weird problem on lead code. The equivalent code of this is in JavaScript. In case you're interested, looks something like this. This language should be JavaScript, but you get the idea. You can describe a number here, give it a type. As you can see, you don't ever tell the TypeScript compiler that this has a bigger size or smaller. Number is the only type here, but Rust gives you a bunch of types to choose from. This is another benefit only. If you don't want to use any of the types, it's fine. But if you want to reduce your memory footprint, if you're only going to use smaller numbers, then just use I8, I16. If you only want to use positive numbers, then just use U8, U16, U32, so on and so forth. Amongst all the things that we have discussed, you might have a question, or you probably should have a question. Okay, what if we ever overflow Harkirat? What if I write code, this is a really big number, even though I'm assigning it to I8? And the answer is it won't let you compile, right? As you can see, the compiler got your error. You are trying to assign a bigger number. You got a red squiggly over here. But what if I write this code? Here I8 is 10. And let's say I write a for loop. Don't worry about the syntax of the for loop. We'll get to it very soon. But if I write something like this, for I in 0 to 1000, x equal to x plus 100. And then, whatever, print x. Excuse me. I already see an error here. The error over here says cannot mutate immutable variable x. We'll be getting to this very soon. You cannot change the value of a variable in Rust unless you explicitly tell that it's a mutable variable. What does mutability mean? We'll get to very soon. But for now, just for this example, bear with me for a few seconds. I've defined a variable. I've just added something extra here, which feel free to ignore. I iterate from 0 to 1000 and add very big numbers here. Now the Rust compiler isn't complaining. Harkirat, why is it not complaining? Why does it not know that this is an I8 and you're adding a lot of big numbers here? So, x will become very big and x will overflow. X will become greater than 127, which is the maximum value that you can store in an I8. Why is the Rust compiler not complaining? Why is it? If I run cargo build over here, you will notice it builds correctly. There is no error. Why? Because the compiler never runs your code. The compiler can do static analysis. If you give it a very big number here, it will be like, oh, you're trying to initialize a very big number on an I8. I won't allow you. I won't compile. But if you have runtime logic, what does runtime logic mean? If you have a for loop, compiler is never running your code. It is statically checking. It's like a viewer. It's like someone who's viewing your code. Now, if someone's viewing your code, they won't actually be like they won't run 1,000 iterations and try to figure out, okay, oh, this will overflow. So that is why the compiler doesn't know. This code pretty much will overflow. And if you run this code over here, you will see the process exits with an error that says attempt to add with overflow. So you can actually overflow variables. The compiler is good enough to let you know, okay, the number is too big. At initiation, it cannot do runtime analysis. It cannot actually run your code. The compiler has no capabilities to run your code and actually figure out that X is becoming very big and it will overflow. So this will be a runtime exception, which is exactly what happened here. Cool. That's enough about numbers. Let's move on to booleans, which is the next thing over here, which is probably the easiest thing here. Very simple, as you would expect. It has two values, true and false, and you can do whatever you want with it, and operator or operator, things like these. If you look at the code that's mentioned here, let me just copy it and bring it over. What does it say? The main function says let is underscore male equal to false, let is above 18 equal to true. You can change these values. If the person is a male, it prints you are a male, else it prints you are not a male. Notice I did not print you are a female because there are many genders, and you should keep that in mind. If the person is male and is above 18, then we print this on the screen. Currently, is this true? No. Let's make this true. Let's make both of them true and then try to compile the code, or actually just run it. Cargo run. And you will see it says you are a male, you are a legal male. So yeah, it's pretty simple stuff as you would expect. Harkirat, can I change it? Can I be like is above 18 equal to false? There was something I told a while back, which is all variables are immutable by default. If you hover over here, what does it say? It says cannot mutate. Mutate means change the value of an immutable variable. So if you ever want to change something, you have to make it mutable. This is how you make it mutable, but we will get to this very soon. Just wanted to show the same thing here. That's it for booleans. Probably the simplest of the lot here. Numbers, if you want, you can complicate, but in the end can become pretty straightforward if you're just using unsigned 32-bit integers, signed 32-bit integers. Booleans, fairly straightforward. Strings are the most complex, primitive data type in Rust. You might say, Harkirat, why? Seems like a fairly straightforward thing. A string, why does Rust not let me do this? Let x equal to some very long string and good to go, Harkirat. Isn't this simple enough? Sort of. You might think this is simple enough, but the problem with strings is they don't have a fixed type. Very similar to arrays or vectors that can change their length. And when you have something that can change its length at runtime, it becomes slightly tricky to deal with, especially when it comes to languages like these. These languages sort of have a concept of heap versus stack, which if you don't know what it is, we'll be getting to it very soon. But the high level idea is if you have something that will change at runtime, the length of which can change at runtime. This is a string. I might want to add some more things here, remove some things from here, make it empty. If something like this is going to happen, if you're going to change the space that a variable needs, this variable can change space at runtime. What do I mean by runtime? I mean if I write a for loop. If I write a for loop for I in 0 to 100 and try to do, ax equal to ax plus some random string. That's it. The syntax is incorrect, but you get the idea. If I try to do this, I have defined a string and I'm going to add more things to the string. You are changing the size of this. You're making this bigger in length, which means it needs more memory from the RAM. Initially, you had a small string stored over here. Let's say, whatever, hello. You don't want to write it here. You had just enough space to store hello, but now you're adding more things here. So you need to ask RAM for more memory, which is why strings become complicated. Harkirat, the same thing happened in numbers. If I do let x equal to 1 and then do x equal to x plus 1, then the same thing is happening here. Why don't I need more space when I define a number? And the answer is, can you guess the answer? The answer is irrespective of how small your number is, If you say it's I32, it will take 32 bits here in RAM. If you add more to it, it is fine. It has 32 bits over here reserved for that integer. That is not true for strings. In strings, if you have defined a very simple string over here with, let's say 10 characters, it has enough space to have those 10 characters. As soon as you append to it, it needs more space in RAM, which gets, unsafe because you're accessing more RAM. You're asking it for more space. What if there is something else right after it? It becomes slower because getting more space from RAM is much harder. And this is where heap and stack will come in eventually. But high level, strings are actually much harder, even though they might conventionally feel like very similar to numbers and booleans. They're significantly different from numbers and booleans. And the most complicated Rust primitive type. There are probably, I would say 3 primitive types: strings, numbers, and integers. What are the 3 primitive types in Rust? Maybe even any language: string, numbers, which can be of 2 types usually, integers and floats, and then finally string, booleans. The last 2 are easy to initialize, change value throughout the lifetime of your program, faster to change value throughout the life cycle of your program, slower to change value, much harder to keep in memory, passing by reference. We'll see what this is, but don't be fooled by the syntax here. So simple, it will not be. Eventually we'll see how this gets difficult. Let's quickly look at the syntax. There are many ways to initialize a string in Rust. Easiest one is this: let greeting equal to string : from whatever your string is. Harkirat, why not simply this? You can do this as well, but you will see the type on the left changes. If I write hello world, the type is @str. Already so confusing. What is that here? And if I write string : from, the type here still seems a little more manageable. It says string, which seems like is a struct over here in Rust. Don't worry about it. Let's not complicate it. Fairly simple. Let greeting equal to string : from hello world, and then print greeting over here. If I run this, what do you think gets printed on the screen? Hello world. Fairly straightforward. This is good. And consider this to be end of this slide. If you're a beginner, move on to the next one. If you're a little advanced, if you want to get a little bit more into the depths of Rust, create some curiosity for what's coming, I have a line commented here. Let's try to go through this line and understand why do people say Rust becomes a pain in the ass if you do it, if you use it for a long time compared to JavaScript. Why is writing Rust code really hard compared to JavaScript? How does it do a bunch of checks at compilation compared to JavaScript at runtime? Also, all the codes that are present here have equivalent codes in JavaScript, so feel free to look at them if you're more comfortable in JS. With that, one strong, again, feel free to move to the next one if you're a beginner, but for all the advanced folks, let's see what I'm doing here. Let's say I say, please print the character at the first index over here, which is H. If I ask you to do that, how would you do it? Harkirat, probably something like this: greetings of 0, println, something like this. Harkirat, is this right? No, unfortunately, it's not as easy as this. Okay, Harkirat, I see your comment. It is slightly harder. Greetings might be a class. It might have a function called chars that gives you all the characters. And then you're doing .nth, which means give me the nth character. And then you're saying 0 over here. So Harkirat, this is the right code. The character at the 0th index is let char1 equal to greeting.chars .nth of 0 Harkirat, and then I can just print char1 Harkirat. Is this right? Notice the type of greetings.chars.nth of 0. It is not char. It is option of char. And if you try to print it, it gives you an error. It says option of char doesn't implement display something weird. So the question is, why does this not run? This code will not compile. If I run this code, it gives you a red error. What is this error and how is this different from JavaScript? First, let's run the same code in JavaScript. Let's see the equivalent code of this in JS. Let's open this up in Replit and let me paste it here. If I run this code, The output over here is nothing. Why is that? Believe it or not, it took me almost 10 minutes to realize I'm not calling the main function. I thought something's up with the applet, then I tried it locally. Did not work, then I finally realized I'm not calling the function. This is what happens when you context switch between a language where there's an entry point function like Rust versus JavaScript. Either way, this is how you call it. Finally, you see hello world on the screen. What if I want the 0th character? I will print greetings of 0. If I run this, it will say H. H is what gets printed if I do a greetings of 0. What gets printed if I do a greetings of a very big number? Basically, run out of index here. JavaScript doesn't complain. It simply prints undefined. This is what makes JavaScript slightly unsafe. It is letting the developer access something that doesn't even exist, not even complaining. Harkirat seems okay to me. Yes, seems okay to me as well. Most applications it is okay. But Rust is strict. Rust says, कि नहीं यार, what are you trying to do? God damn it. What are you trying to do? You are trying to get something at the nth index of a string. But how do I know that something exists over here? If you're trying to get the 100th character, it might be a character, it might be nothing as well. So I will not return character. The type of this is not character. It is option of character. What is option, Harkirat? We will get to when we reach enums. But the point is, okay, you can't simply print undefined here. It doesn't let you have undefined types or print them. It says, bro, are you sure this is a string? I am telling you it is not a string. It could be a character, it could be nothing as well. So if you're trying to print it, make sure first it is a character, and only then will I let you print it. How can we make sure it is a character? There are multiple ways. This is the easiest, which is, you can do something like this. If you don't understand this code, it's fine. We'll reach this when we reach pattern matching. So feel free to ignore as well. But the point is, the Rust compiler does not let you assume that the type of this will be character. The Rust compiler says, bro, the type of this will be optionally a character. And if you want, you can either print the character in case something exists. That's what sum means here. If nothing exists, you can print something like this. This I will allow you to do. I will not allow you to do this. Okay, the character is, char1. This I will not allow because I want to let you know as the developer, okay, you might be writing some unsafe code here. You're assuming this is a character, but it's not. It's optionally a character. It could be nothing as well. So that's sort of, the things that get frustrating over time. As you have to realize, oh shoot, this is not returning a character, it's returning optional character, which is good. It's actually good. It's telling you upfront, okay, bro, you might be running into some issues here. This is not a character, it's optionally a character. Please make sure, you're not messing things up. So yeah, that's a brief about options and how it's so easy to write code sometimes in JavaScript, which you see on the left here. Oopsie daisy. And much harder to write the same code in Rust because Rust is like, no, bro, this is another way for you to write this code. If you can unwrap an option, this will throw an error, a runtime error if nothing exists over here, which basically means if I run this with index 1, it'll work. There will be no runtime exceptions. You see character is E because that is what exists at the index 1. But if I run the same thing with a very big index which doesn't exist, then cargo run will pretty much, the thread will panic, which means you'll have a runtime exception. If you use unwrap, so you should generally avoid unwraps. What is an unwrap? We'll get to eventually, but this is just another way to print the thing. And what's the better way to print? When you're writing unwrap, you're literally telling the compiler, okay, yaar, bro, it's okay. I'm okay with the runtime exception if it happens. But again, we will get to this eventually. Probably the cleaner way to look at it is pattern matching, is what appears over here. With that, I think that's enough for this section. Let me open the slides again. Let's move on to the next section, which is called conditionals and loops. We have all simple stuff. We won't be spending a lot of time here, but just to check it off the box, let's understand how do you do if else's and how do you do loops in Rust. All right, conditional loops and functions, thankfully something we can just sprint through. Conditionals pretty much represents how do you do an if and an else. And it's very similar to JavaScript. You just don't need brackets in here. You can add brackets if need be. But other than that, as you would write a function in JS, which looks something like this. For example, if you have pretty much something like that. You can remove the braces here, as I said. You can keep them as well. It'll just give you a warning if you do that. But other than that, as you can see, it's a simple if statement. Similarly, if you want, you can have an else if as well. In case you have multiple conditionals. If you've done this in any other language, it's pretty much the same. Only thing is, unless you have something too complex here, you don't need the brackets, which I'm going to remove. And then the warnings that you see here will go away as well. So if I rerun this now, you will see it says the number is even without any warnings. If I do add braces over here, I can see the warnings by hovering over this yellow squiggly. I can also, when I run this, it'll give me a warning. It'll also tell me how to fix it. So yeah, nothing out of the ordinary, fairly straightforward stuff. That's if and else's. The next thing is loops. The way to do a simple loop, let's say I iterate from 1 to 100, is for I in 0 to 100, and then do a whatever println I. If I do this from a 0 to 10, what do you think gets printed? Do you think 0 to 9 gets printed, or do you think 0 to 10 gets printed? 0 to 9 gets printed, which pretty much means this is what you need minus 1. So if you put 10 here, the iterations run from 0 to 9. They do not run for 10. If you need it to run it for 10, you need to put 11 over here. That's how you do a simple loop. Other than that, you might want to iterate over a bunch of things. What is the thing that you usually iterate over? Arrays and maps, if you have them, or strings. These are the three things you would usually want to iterate over. For example, if I ask you to write a function, that will give you the first underscore word given a sentence which is of type, let's say, string, even though this will probably create errors. Let word equal to, or whatever, sentence equal to my name is Harkirat. And if I do a let first word equal to get underscore first underscore word of sentence, I pretty much need this get first word function to iterate over the sentence, pretty much go letter by letter, and figure out where the first space is, and then return everything below it, before it. So here I need a for loop to iterate over this string, right? So first of all, let's make this a string rather than it being a @str, which is the current type. Let's print the first underscore word over here. It's giving me an error because this doesn't return anything. So let's discuss functions while we're at it as well. This is how you define functions, which might seem pretty straightforward. The keyword fn followed by the name of the function followed by the arguments along with their type, very similar to TypeScript. The only thing is, very similar to TypeScript, how you also have to give the return type here. You have to do the same thing here by giving an arrow. So pretty much something like this. Get first word returns a string. Now, if you want, you can iterate over all the strings. This is a more complicated way of doing it. So let's see if there's a easier one. For I character in sentence dot chars. Yeah. If chars equal to empty string, then break let answer equal to string : new works, or if that seems slightly jarring, you can do a from empty string, and then here you can be like answer equal to answer, or answer dot push underscore character. There you go, and then you can return the answer over here. Does not exist, so push underscore string character. How can you push a character to string? Cannot mutate it. You need to make answer a mutable string. So this is how you can iterate over characters. This is actually extremely deep. If you actually go through what's happening here, is that sentence.chars is actually returning you an iterator of type is returning your struct which has an iterator, which has all the bytes that it's iterating over. So what's actually happening is, just to give a brief, but like feel free to ignore this if you don't understand it. Strings are actually stored somewhere in a place called heap, which we'll be going through very soon. And they're sort of stored as contiguous memory elements. So it's like byte after byte. And you can iterate over each and every byte by using iterators in Rust. That's what's happening under the hood. But let's not go there just yet. This is a simple for loop that lets you iterate over iterators. We'll be getting to iterators eventually. So even if you don't understand this, it's fine. You can actually simply worry about simple for loops which let you iterate from I to n, where n is a number, which is what you'll mostly need in a lead code like application. If that's what you're aiming for by the end of this video. Okay, I should be able to at least solve lead code problems in Rust. Then a for loop like this, for I in 0 to whatever n your number is, let n equal to a very big number. Then print hello world, whatever. This for loop is great. And similarly, there are while loops. Firstly, let's look at the for loop again and try to compile the code. Let me remove. Let's also run the function over here. We never ran it. We just wrote it. Might not work. I did a few things here. I added an underscore here because it was giving me a warning that said I've defined this, but I have not used this. As you can see, I'm not using I here at all. So I can use it, in which case the warning will go away. Or I can prefix this with an underscore. Okay, I know what I'm doing and I don't need to use this variable at all. If I run cargo run, you will see a bunch of hello worlds followed by my first word is my, which is exactly what my first word is over here. If I change this to Harkirat, name is Harkirat, and if I rerun this, as you would expect, the first word is able to extract out as Harkirat. If there is no word, then also I think the logic works. If there is no other, there's a single word basically, the logic still works. It says first word is Harkirat. So that's how you define functions. Functions get very complicated when it comes to taking arguments. This is where something called ownership comes into the picture, but totally forget about it for now. Don't worry about that just yet. As I said, iteration, you want to worry about iteration in arrays, maps, and strings, but for now, we're worrying about simple iterations. And if you want to get a little fancy, this is how you iterate over a string. But if you don't understand this for now, it's fine. Yeah, it'll be a long while before you understand how iterators work, and especially how do you iterate over a vector or a string. But you don't have to internally understand how this works just yet, or even at all for a long time. As long as you understand the syntax, as long as you can Google how to iterate over a string in Rust, and you get the answer. For I, C in my string.characters.enumerate, which is another way you can iterate or use this iterator over here. We have done for char in sentence.char, so you can also do sentence.chars.enumerate to basically get the character as well as the string. That works as well. This works as well. This is what we have done. This is the other thing that you can do. As long as you can Google, you're fine. You don't have to get into the internals of iterators, although as you get into advanced strings and how exactly is string stored in memory, this should sort of become obvious what's happening here. With that, let's move to the next section. What is the next section? We've done conditionals. We've also done functions. So there's nothing too difficult to explain here. This is how you define a function. So the only new thing to learn here for you might be, okay, you have to define the return type as well. So if I have a do underscore sum function, as you can see, it's returning an i32 as well and taking, of course, two i32s as input. If I do a let a equal to 10, let b equal to 10, let sum equal to do underscore sum of a comma b, and then try to print it, it just works. If I don't give it this return type, it will not work. So you need to specify the return type of any function whenever you're defining it. It cannot be inferred like you can in TypeScript. In TypeScript, the return type can be inferred. Here, the return type cannot be inferred. So when you're defining a function, along with the arguments that you're taking as inputs, you need to give the return type. Harkirat, we haven't discussed arrays. We haven't discussed vectors. We haven't discussed objects like objects in JavaScript. When will these come? These will come after we understand memory management in Rust. That's what the next section is going to be, which basically means we've reached here. Now we're coming to the slightly teachy and probably slightly overwhelming part, which is memory management in Rust and a few jargons. Then we'll get to all the things that you were talking about, structs, enums, vectors. But yeah, the next few sections will boggle your head, even if you don't understand them completely. That's fine. Until this point, I would urge you to create a few functions, write a few loops, do a few conditionals, play with strings and integers, and go from there. Let's move on to memory management in Rust. But more importantly, how does memory management happen in various languages, not just Rust? All right, memory management in Rust. In the next few sections, we'll be going through some core concepts in Rust that make it more memory safe compared to a language like C. We'll understand how does memory management happen in 3 set of ways: the garbage collector way, the manual way, and the Rust way. Why is it different from these two, and what makes it extremely safe? Let's get right into it. Before we understand Rust specific concepts, let's generally understand what does memory management mean. What does memory mean in the first place? Whenever you buy a machine, let's say a Mac machine, a Windows machine, the few things you look at are what is the processor like? Is it an i7 machine? Is it an i5 machine? How many cores does my machine have? Is it a 10 core machine, 12 core machine, 16 core machine? And what is the total hard drive space? Is it 1 terabyte, 2 terabyte? How much images can I store? And lastly, the RAM that I have. What does RAM stand for? Random access memory. This is something you optimize for because all the programs that you run, for example, currently I'm running Chrome, I'm running a bunch of other softwares here on my Mac machine. All of these need to put some data in random access memory. Harkirat, why do they have to put it here? Why can they not put it in SSD, the 1 terabyte thing I have? The answer is you can store a bunch of offline things here. If you download a GTA game on your machine, the binary of the GTA game is stored over here. But when you double click on it, it needs to execute, and execution happens inside RAM. If I'm running a browser right now, and let's say inside this browser, I do something like this, where a equal to 100, then this variable just got created here in my random access memory. So all your programs that are currently executing need some space here based on how heavy the program is. And the way to put data in here, the way to get some space here, considering there are so many programs fighting over space here, is sort of difficult and complicated. If you're using C or C++, they give you very nice direct access to RAM. You do manual memory management there. If you're using a language like JavaScript, then JavaScript's garbage collector takes care of memory management. But if you do Rust, something new happens. Let's understand how all 3 of these languages do memory management. Whenever you run a program, be it C++, Rust, or JavaScript, it allocates and deallocates memory on the RAM. For example, if you run the following JavaScript code, very simple JavaScript code, we call a main function, which calls a run loop function, inside which we initialize an empty array, we push a bunch of elements to it, and then finally we log the array over here. When you run this, the control reaches here, goes inside this loop, and a X variable is created that is initially empty, but eventually becomes very big. Where is all of this data stored? Where is the X variable stored that's now sort of significantly big? It's stored here in the random access memory. Some part of the RAM it takes and gets stored here. What happens when the function stops executing, or the control reaches this bracket, let's say, or let's say there was a console.log after it, the control reaches there. You no longer need X. X needs to exist inside the scope of this function. So even though you had to allocate a lot of space to X here inside RAM, as soon as the function execution stops, you move out of scope, X can be garbage collected. X can be deallocated from the space. The JavaScript program can tell the machine, okay, yaar, I know I needed this much space for X, but I don't need it anymore. So feel free to take it back and give it to a different program. They can use the memory for doing their own thing. That is how JavaScript does memory management. It has the concept of a garbage collector. written by some smart people. If you use JavaScript or even Java, both of these use garbage collectors for memory management. The name itself says what? Garbage collection. What is garbage? If you look at it, this X variable is garbage after the run loop function stops executing, right? After the control reaches the next line, you don't need X. So wouldn't it be nice if you had a sweeper, a garbage collector, going through all the variables that don't need to be allocated in memory anymore and garbage collect them from RAM. Tell the machine I don't need this anymore. That is the simplest way to do memory management, the way it happens in JavaScript. Usually no dangling pointers or memory issues, since the developer, Harkirat, whoever is writing the JavaScript code, cannot do memory management, cannot access the memory directly, cannot say I want 10 bytes over here, give it to me, or I want to access this space in memory. The JavaScript developer can never do this. You can never go to your console and be like, where memory data equal to ram dot memory dot location, some random location in memory. Give me all the data that's present here. Cannot do that in JavaScript. Cannot do any memory management in JavaScript. Harkirat, can you do it in other languages? Yes, you can. But here you cannot. You can't do manual memory management. And examples of languages that use garbage collection include Java and JavaScript. This is like enough to know about memory management in JavaScript. You never worry about, is my variable still in memory? Am I going to go through dangling pointer issues or memory issues? Unless, of course, you're creating an infinite loop. I mean, if you create an infinite loop here, then of course your program will run out of memory. If you write a recursive function that keeps calling itself, then of course your program will eventually run out of memory. But if you're not doing anything out of the ordinary, garbage collection is taken care of, memory management is taken care of by the garbage collector. That's the first set of languages. This is one of the reasons that they're simpler to write, because you never have to do memory management by hand. The developer does not have to write the code to do this. What is the second category? Manual memory management, the most difficult bit. This is why it's harder to write C. This is why also trading firms use C, because they want to access memory. They want to, allocate space here themselves, and the developer wants to write that code. C lets you do that. You allocate and deallocate memory yourself. If you've heard of malloc in C or calloc in C, it lets you allocate space here. Give me 20 bytes. I want to point to these 20 bytes here in the RAM. And it gets complicated. This is the reason pointers are so difficult. If you're ever doing C++ and you're doing it for competitive programming, you don't have to deal with pointers, thankfully. But if you go through a CS class where you have to go through, the fundamentals of C and C++, is when you deal with pointers, and that's why they become slightly complicated. Rust also has a concept of pointers. We'll be coming to them very soon, but that's what makes, manual memory management a little weird. Chalo koi nahi, let's say you are able to do memory management manually in C very well. You are a very good developer. You understand how to allocate and deallocate memory yourself. The second problem that comes is can lead to dangling pointers / memory issues. There are a bunch of common memory management issues that happen if the developer is writing the code, because developers are dumb. Whoever has written the garbage collector, some really smart people, has been audited well. There are no memory leaks usually in, a compiler for JavaScript or Java, because it's been written by some really smart people. They make sure data is collected correctly, or garbage collection happens correctly, memory gets freed correctly. Here, a random developer writes code. They are able to allocate memory, deallocate memory. This can lead to a lot of runtime issues. Things like dangling pointers, if you've heard of them. You have a variable pointing somewhere in memory. You have a variable pointing somewhere in memory where there is no data. If you've heard of buffer overflow issues, you can, since C programs have direct access to memory, they can overflow a variable, let's say an array variable, and read data that's, not of this program, but of a different program. Very common, CTF attack vector. So C is great, but it has these problems. Very commonly you'll hear memory management issues and, dangling pointers, race conditions, things like these. Learning curve is high since you have to do manual memory management. Might be another very commonly, if you have tried to do C programming, you already know this. If you haven't tried doing C programming, there is a decent learning curve. The same is in Rust as well. But here it's not just the learning curve of understanding memory management, it's also a lot of learning curve of writing code to do memory management. You don't have to do that in Rust. And examples of this are C. So we've understood two types of languages which have a garbage collector. Great. They do memory management themselves. The developer doesn't have to worry about it. Here, developer has to worry about it. The developer has to allocate and deallocate memory. The Rust way. Rust said, what C does is great. We can allow that, but let's add some rules on top of it so that you don't run into things like these memory issues, dangling pointers. The program becomes memory safe. What does Rust say? Rust says you can still do manual memory management even over there, even though most people don't do it. You rarely write code to do manual memory management in Rust. It said we will allow for pointers, we will allow for dynamic data during runtime, but there are some rules you have to follow. These are the rules we will understand. And if you don't follow these rules, then your program will not compile itself. Forget running, it will not compile itself. Why did they add the rules? Rust has its own ownership model for memory management. Why did it add an ownership model? It said here there are common reasons why these issues happen. We will avoid these issues at compile time itself. We will not let the developers write code that could lead to these errors. So Rust forces you to write code in a way such that you cannot, there is a very low probability, if at all, of any of these memory issues happening. That's what makes it memory safe. Makes it extremely safe to memory errors. That is sort of, the moat of Rust. They said you can write normal code. You can also get access to memory if need be, but follow some rules. What are these rules? We'll be coming to them in the next slides. How do they make it memory safe? That also we will discuss as we reach the slides to come. What have we discussed until this point? 3 types of languages: garbage collector languages, manual memory management languages, and the Rust way, which is, unique in itself. Memory management is a crucial aspect of programming in Rust, designed to ensure safety and efficiency without the need for a garbage collector. You might say, Harkirat, why not just do this always? Garbage collection is great. The user doesn't have to worry about memory issues, or there are no dangling point errors over here. That is true, but garbage collectors are slow. It is a whole process that's trying to figure out, there is this variable that went out of scope called X, so let me garbage collect it. So it makes the language slow, which is why you want to avoid it or that's one of the reasons that Rust sort of does not do memory management that way. Not having a garbage collector is one of the key reasons why Rust is so fast. It achieves this. I said there are a few things it provides. Ownership model is one, but a bunch of other things. What are these things? Mutability. The way it does memory management, heaps and memory, this should not be memory, this should be a stack. Ownership model, borrowing and references, and lifetimes. These are the buzzwords for us to learn next. Mutability is actually fairly easy. Heaps and stacks, this should be stack, is actually a common way to store memory. It isn't one of the reasons that it is fast. It's just how Rust does memory management for various types of data, be it strings or, integers, booleans. Ownership model is something Rust specific, slightly harder to understand. Borrowing and references is also Rust specific. References aren't Rust specific, but the way references are done and borrowing is done is Rust specific. Again, slightly difficult. Lifetimes are, they will go over your head, so we will not be discussing them today. But these will come in part 2. This is also super important to understand how it's able to manage memory so well. How is it so efficient also, fast also, yet can avoid all of these issues. Let's start with the simplest one, mutability. Jargon number 1, mutability. You might have already heard of this. If not, let me share what mutability means. Immutable variables represent variables whose value cannot be changed once assigned. Have you guys heard of constants in JavaScript? What happens if I run const a equal to 1? And maybe b, I already had defined a. So const b equal to 1. If I try to assign something else to it, it throws an error. What does it say? Type error, assignment to a constant variable. So we can say b is immutable. That isn't technically true, because in JavaScript you can actually do this const c equal to empty array, and then you can push to an array, even though this is a constant, you can still push values to it. So it's not exactly immutable. You can still update it, but you get the idea. You get what immutability means. Very similar to a constant in JavaScript. Immutable variables represent variables whose values cannot be changed once assigned. And by default, all variables in Rust are immutable. I repeat, everything is a constant. Once a value is assigned, you cannot update it. Let's look at the code over here. If I run this code over here, even without running it, you see, a red squiggly here, which tells you there's a compilation error. What does it say? Cannot mutate immutable variable X. It says here X is immutable. Harkirat, I have not written const here. I to wrote a let. Let should mean I should be able to change the value of it. No, this is not JavaScript. This is Rust. Everything is immutable. What is immutable? It means cannot be changed. So you cannot assign anything, even if this was a, string. Hi there. And you try to push something to the string. x.push underscore string, something random, it will throw an error. It will say cannot mutate immutable variable X. So irrespective of if it's a string, if it's a number, whatever it is, you cannot update its value by default. You can set X to be mutable by saying let mute X equal to something. You can explicitly tell the Rust compiler, okay, hey, I want this variable to be mutable, and then it will compile. But by default, everything is immutable. Why Harkirat seems pretty dumb? It might seem dumb, but mutability leads to a lot of memory issues. Very simple example of this might be, what if there are two threads, in case you've heard of threads, in case not, that's fine. But let's say there are two threads trying to read the same data somewhere, and the value of this data is 1. If the data variable is immutable, they can freely access data, does not matter. But if it is mutable, then one of the threads might update it to 2, while other one is reading it. So the other thread might get back the value 2, or might get back the value 1. So there can be a race condition. Immutability assures that doesn't matter how many threads are trying to access it. There is no possibility of a race condition. It can never happen if something updated its value. It is immutable by default. So that is one of many reasons. Rust is like, no, I'm sorry. Everything is mutable. Everything is immutable. Unless you explicitly tell me a variable is mutable, I'm going to assume it is immutable. That is the very first property of variables in Rust, that they are immutable in nature. If you do want to update them, you need to add a mute over here. By default, all variables in Rust are immutable because immutable data is inherently thread safe. Because if no thread can alter the data, then no synchronization is needed when data is accessed concurrently. If both the sides try to access data at the same time, there is no synchronization needed. You wait, I am first trying to update it, or you wait, I will first update it, then you take data. There is no need for a synchronization. By default, the data can be read by anyone, doesn't matter who reads first, the data is constant, can't even change. Knowing that certain data will not change allows the compiler to optimize the code even better. If the compiler knows that this data is not going to change, it doesn't have to worry about a bunch of compile time checks. It doesn't have to worry about, what if there is a race condition here, I should wait over here and not wait over here. By default, makes the compiler or the final binary much faster. Harkirat, but what if I make everything mutable? What I will do is, you said this is a benefit, I will make every variable mutable. Yes, you can. It will take away all of these benefits. So it's not like it's forcing you to have immutable data throughout, but it's by default telling you, unless you need it, keep it immutable. If you really need to change the data, then it's fine. Set it as mutable, but generally avoid mutable variables unless absolutely necessary in Rust. You can make variables mutable by adding mute over here, the mute keyword. Constants in JavaScript are not exactly the same as immutable variables in Rust. In JavaScript, you can also update the contents of constants, even if it's an array or an object. Even if it's a constant, you can update its value, just how I showed a while back. If I define a constant over here, const arr1 equal to empty array, even though it's a constant, I can push some value to it. So it's not technically immutable. I can still mutate data there. And this isn't a Rust specific concept. Immutability is something that even JavaScript sort of approached / accepted / wanted in the ecosystem. In fact, I remember one of my bosses used, like back at Goldman, one of the UI guys used to use this library very heavily or promoted very heavily. Immutable collections for JavaScript. It lets you basically create immutable variables in JS. Immutable data cannot be changed once created, leading to much simpler applications for development. No defensive copying, don't know what that means, but you get the idea. This immutability as a concept is not just specific to Rust. It's something a lot of languages try to adopt in various forms or fashions, be it either through an external library or otherwise. Rust just enforces it by default. Here, by default, this is a immutable variable. You cannot change its value. If you do want to change its value, it's fine. You can mark it as mutable, but I would by default mark it as immutable. That's what the Rust compiler says. That's the very first Rust concept that they enforce, and that makes it faster. This is the easiest one. The next jargon is where things are going to get hard. Actually, not next. Stack versus heap is also fine. The ones that afterwards make it slightly harder. But first, let's get into stacks versus heap. How does Rust actually under the hood do memory management? All right, stack versus heap. If you've done a little bit of C++, you probably already know this. If not, that's fine. Let's cover it from the beginning. Let's look at the photo. Stack on the right looks much organized. Things stacked on top of each other. Heap looks heavily disorganized. Everything thrown together. No easy way to find something. Let's say, there's a piece of paper here that you really need. Very hard to find where it is. Versus here, if I give you a constraint, you have to put things on this stack and then only access the thing on the top and then pop things off. This is much more easy for you to organize and access compared to this. If I give you a heap and throw a bunch of papers in and I tell you, give me the paper that's a court judgment from a specific day, you will have to look through them and find that out. Versus here, if I tell you, hey, push court judgment from 1st December, 2nd December, 3rd December, so on and so forth, up until 1st January. And here I say, okay, return me the 1st January code judgment. You'll just pop it off the top. Then I say, okay, give me the 30th December judgment. You'll pop it off the top, so on and so forth. So stacks seem much more organized compared to heap. But what is stack? What is heap? Why am I even calling or using these buzzwords? Rust has clear rules about stack and heap data management. Again, this statement gave you nothing. Let me explain this with a diagram. This is a very big machine. Let's say a Mac machine. It has random access memory here, RAM, that a lot of programs can access. This RAM currently on my machine is being used by this Google Chrome and a bunch of other applications. So whenever you start a Rust process, this Rust process will also need some part of this RAM. It will be like, yeah, please give me this much. This is a very heavy program that I'm about to run. So I will store my variables here. Please give me 5 MB of space, let's say. So the RAM is like, okay, take 5 MB of space. And this is what I'm calling stack. Harkirat, so you are saying, okay, whenever a Rust program starts, it will tell the RAM, give me some space. RAM will be like, okay, there you go. This 5 MB is yours. And Rust will push variables here. And that's how it does memory management. That's how Rust does memory management. If I define a variable here called let x equal to 1, or x colon I32 equal to 1, then this x variable, Harkirat, you are saying will get stored here in the stack. Yes, it will get pushed to the bottom of the stack. Okay, there is a x variable over here. Then Harkirat, stack is good enough, right? What is the other thing you're talking about? Heap. What is this heap and why do you need that? I will just ask the RAM, give me some space, get it, and start to push variables here. You are saying, if there's an x variable, it gets pushed. You might mean, if I define another y variable here, which let's say, is a Boolean, equal to true, then I can just store the y variable right above it. This isn't true. The data doesn't get stored in a heap like this. We will be discussing very soon how it gets stored. But assume for now that is what happens. So stack is great, a place where you can put all of your variables. If you ever access it, if the developer ever writes print x, then it will just find it from here and print it on the screen. The problem is some variables are fixed at compile time. Some variables can change. I repeat, some variables ka length is fixed. For example, if I define an i32-bit integer, it only needs 32 bits. So I can say amongst these 5 megabytes, I will take 32 bits, which is what? 4 bytes. I will take this much and let other people access whatever they want. My i32 variable, my x variable only needs this much space. You have fixed compile time space, fixed runtime space. You can predict, okay, yeah, this will only be this much. Same for a boolean. Boolean also needs 1 byte, I think, not 1 bit, 1 byte in a Rust program. And it never changes. As the program grows, even if you make this number very big, let's say, 100,000, it will still be stored in a 32-bit, in those 32 bits. If you make it really small, still be stored in those 32 bits. The problem comes when I define a third variable called let z equal to a string. If I define a string, can I predict the length of this? Do I know what the length of this will be? Yes, Harkirat, you have written 3 numbers, so it will be 3 bytes. Just store it here on the stack. Create z over here, and then point this over here. This might sound true, but what happens if I do this? What happens if in the next line I'm like x dot push a very big string? I'm changing the length of z. Sorry, this should be z. I'm writing x again and again, but you get the idea. I'm changing the length of z as time goes by during runtime. So the compiler doesn't know. Compiler is like, bro, when I compile the program, I can't really predict what if you put this push underscore string inside a for loop, which runs randomly. It might run once, it might run 100 times based on some random variable. How do I know at compile time? If this is the program that you're running, let's say, let me copy this and bring it somewhere on the side. Whenever you compile this program, if you run cargo build, the Rust compiler says, bro, how do I know the final binary, what the length of the z variable will be? How the z variable could be, okay, you might say, Harkirat, it will be 3 bytes here plus a bunch of bytes here. But what if the second thing is inside a for loop for I in 0 to some random number, which random number can only be decided at runtime. It cannot be decided at compile time. When your program is compiling, this code doesn't run. This line of code, this for loop, will not run during compile time. So how does the compiler know कि यार z की length will be 3, or will it be 3 plus 8, or will it be 3 plus 8 plus 8? It doesn't know how many times this line of code will run. So it cannot predictably put z in the 5 MB because the length of z can grow and decrease in size. It cannot be like nahi z to itna hi hoga. And this is where the heap comes into the picture. The heap, as the name suggests, is a place where you can put a bunch of random data. It is disorganized data that looks like this, and a string or any variable whose length can change at runtime. A vector is a good example of this, or a dynamic array, or a string is a great example of this. Okay, they can change at runtime. So you don't really store their value here on the stack. You store something else on the stack which points to something on the heap. Nahi samajh aaya? Did not understand it? Let's write this code again. Let's create the diagram again and understand this better. Let me quickly revise. I said whenever you define, let's say your program looks like this, the way memory management would happen, the way Rust would store your variables would be, when you start the program, it will get some space in the RAM, it will name it the stack, and it will push data there. Okay, yeah, there is a x variable, there is a y variable, let me push these here. And then lastly, when you create a Z variable, right, which is a string, unfortunately, you can't store it completely in the stack because you don't know predictably the size of the string. It can keep on increasing, and hence you don't store it here. You store it in a place called the heap. Now, what is the heap? How does this data get stored? Let's discuss that one more time from the top. Rust has clear rules about stack and heap data management. Stack, fast allocation and decallocation. If you put something in the stack, it comes back to you really fast. You can ask for it really fast. You can put it there really fast. Fast allocation and deallocation because you own this space. When you put things on the heap, you actually have to ask the operating system, hey, give me 5 bytes. I need to store some string here. And then let's say you increase the size of the string. Then you have to ask for more. Please give me some more. So this is much slower compared to storing things in some stack that you already own, which means fast allocation and deallocation. If you're creating integers, it is much faster in Rust compared to creating strings. Rust uses the stack for most primitive data types and for when data where the size is known at compile time. At compile time, when the compiler is running, it can predict size is 32 bits, size is 1 byte or 8 bits. Cannot predict the size of this. If I put a for loop after it, which runs this line, second line randomly, at compile time, it doesn't know how long this string would be. Harkirat, what if I write a for loop here that adds more data to X? That is fine. It will still remain 32 bits. X is 32 bits, even if you store 1 here or you store 1,000,000 here. It is still reserving 32 bits over here. So if you put it inside a for loop, the size will remain the same. The value, of course, increases, but the number of bits that you need to store either 1 or 1,000,000 or even, whatever, 5,000,000 is the same. In the end, it's 32 bits that you have sort of, reserved in RAM, and then you're replacing them with 0, 0, 0, 0, 1 or 0, 0, 0, 1, 0 based on what the number is. The number of bits are reserved and they're the same. That is not true for a string, which is why strings are stored on a heap used for data that can grow at runtime, such as vectors or string. This is where you put a bunch of data that can grow at runtime and the compiler cannot predict the size of them. This is where you store a bunch of data that is predictable at compile time. It is an integer. It is going to be 32 bits only. What is stored on the stack usually? Numbers, where you have predictable sizes at compile time. Booleans can only be true or false. And fixed sized arrays. We'll come to what this is later on. You can actually define arrays that have a fixed size. You cannot grow them or shrink them in Rust. They're also stored on the stack. What is stored on the heap? Strings and vectors are good examples of things which will grow or shrink at runtime. So you store them in the on the heap. Let's understand this slightly better. Let's go simple code to hard code and understand how would memory management happen here. I said a small lie over here. Whenever you have a stack, you don't push variables one by one. You push something called the stack frame, which means if this is your stack, whenever a function is put on the stack, whenever a function is called, you put a stack frame over here inside which you put all of your variables. So it's not like if I had 3 variables here, they get pushed one over the other. They get pushed in the same stack frame, which is, one frame for a function. If I have a single function here called main, inside which I've defined a variable which is 32 bits, I will first create a stack frame where I will put all of these numbers, the number here being num. So this is the most straightforward code and how it does memory management. It does not need to touch the heap at all, does not need to store any data on the heap. Just define a variable, and that variable, whenever the stack frame is pushed, will get put here in the same stack frame. But if there are 2 functions and the first function is calling the second function, then things changed a bit. Firstly, when this code runs, the control will reach here. The first stack frame will get pushed. This is the stack frame for the main function, and you will put your data there. Then print underscore num will get called. When print underscore num gets called, this thing gets pushed on the stack. The thing that actually gets pushed is the second function or the stack frame for the second function. Here, this specific function is now called. We'll push this and store all of its data over here, which means currently, since it does have a num variable, whenever you have a number and you pass it to a function, it gets copied here, and you have, another instance of that same number. It's not passing it in by reference, which is why we have another 32-bit number that's stored here on this stack frame. And then eventually when this function execution succeeds, this whole frame gets popped off, and then you reach back to the original main function. So when the control finally reaches here, print num function's execution stops, the stack will look something like this. So what does the stack look like in stages for a code that looks like this? First, main gets pushed, which has your simple integer data. Then print num gets pushed, which has your simple data. Above it, it has the second stack frame, which also has simple 32-bit data. No need for a heap. And lastly, this gets popped off, print num gets popped off, and control reaches here. Eventually, this will also get popped off the stack, and the program execution stops. This was pretty straightforward. You have a stack. If you did not have data that grows or shrinks at runtime, this is great. But what if you have data that can change at runtime? What does runtime mean? It means when you're actually running the program. What does compile time mean? When you're compiling the program. If you're running cargo build, which actually converts your Rust code into the binary, then this is called compilation. If you run cargo run, this does both build and run. But if you just run the binary ./target/debug/program, then this is actually running the binary. And anything that changes its space unpredictably during runtime needs to be stored on the stack. Strings are a prime example of this. So let's look at this code. I write let s equal to string : from hello, and then I print it. Very simple, nothing too complicated. Harkirat, यहाँ पे तो I can see this is a fixed length string and you are not changing its length. I can just store it on the stack. No, unfortunately, even if you can see कि हाँ, this is a constant string and its value is not being changed, it only needs 5 bytes to store data over here. You still cannot store it on the stack. The compiler will still be like, yeah, I don't know if this will grow or not during runtime. What if there is a for loop here that iterates randomly 1 time or 2 times or 5 times based on what the random number's value is, and adds more data here? I will not store it on the stack. I will store it on the heap. I will ask the memory, I will ask the operating system, hey, I need some space. I want to store a string. Please give me some space over here, some contiguous space where I can store something like this. The first byte will have H, the second byte will have E, L, L, O, and that is what is being stored on the heap. What is the heap in the end? The heap is just some address in RAM, right? If this is your Mac machine and this is your RAM, as I said, RAM is very big. And is being shared by, it's not very big, it's 32 GB for example in my machine. It's being shared by a bunch of programs. So if a Rust program doesn't know what the size of a string is going to be at runtime, it will be a very bad idea for it to be like, bro, I have a string, give me all of the space here, because string can grow indefinitely. No. What it will do is, it will say, yaar, theek hai, I know I need to store a string. So it will ask the operating system, okay, yaar, this is my stack. I know there is a stack frame over here, which has a variable that needs to point to something in another location in memory, which is the heap. It asks the operating system, okay, yaar, please give me, I want to store hello, so please give me 5 contiguous bytes where I can store H, E, L, L, O. And the thing that I'm going to store in the stack is the address of the first H variable over here. If I know the address of the H variable, from here I can reach E, it'll just be 1 byte ahead. I can reach L, L, O. So what does the Rust compiler say, or what does, memory management in Rust or even C says? It says, yeah, if you have something that grows and shrinks at runtime, this is how it is stored. There is still something stored on the stack, but it's not the actual value. The actual value is stored on the heap because this might grow. And when it grows, you can just ask the heap for, more contiguous segments over here. If it's not present, you can ask to move this data somewhere else and change the pointer. But you can't do the same thing in stack. Stack is not for growable and shrinkable data at runtime. It's for predictable compile time data. And if you know it's a string whose data can be changed, you don't store it here, but you do store something here. You are still storing the pointer, which means the address to where it's actually stored. What is stored here in the variable? The address to the specific h, the very first h, the very first byte where this is stored in RAM, and then the length and the capacity. How long can this string be? The capacity is 5 here, but you can ask for more. If I do a s1.push_str, I can ask for more data here, and capacity here. But what does length mean? It means how many bytes are currently being used by my string. And what does capacity mean? It means how much more can I store here? And if I do a push_str, I'll ask the operating system, please give me more space. I need to push world over here as well. I will increase my capacity and I will increase my length. And I might change my pointer if the operating system says, sorry, I don't have enough space here, so let me move you somewhere else. The operating system could totally be like, nahi yaar, yahan pe to nahi hai. If you want to push more things, sorry, you will have to move your whole string over here. This is what makes the heap slow, because you're asking the OS, I need some more data. I need some more place to put my strings. Sorry, the developer wrote some code to, make the string go from hello to hello world. So this is what the purpose of the heap is. If you have growable/shrinkable data, just put predictable data on the stack. The length of all of these is predictable. This is length. This will be some 32-bit, 64-bit. This is capacity. This will be 32-bit, 64-bit. Some predictable number, because this is a number. This is a number. The pointer also, in the end, if you have a RAM that's 32 GB, the number of addresses that you can have here is limited. So the size of this is also known. The size of this is also known. The size of this is also known. So you can store this whole thing, which has, 3 things together on the stack, because the size of this thing is predictable. The pointer is just an address, a number effectively, to where in RAM I can find this. I can find the actual string, and hence, the size of this is also predictable. All 3 of these are predictable sizes. You can push them on the stack. That is how memory management happens for strings. Nahi hua clear? If it's not clear, let's look at some more examples. Let's look at, this is a little too big of an example. Let's try to go through this example. Let's see what would happen if I write code like this. There is a function called main that first calls stack_fn, which if you look at it, defines 2 variables, adds them and prints them on the screen. Next, we have a heap_function, a function that defines 2 strings, joins them, and then logs them on the screen. And lastly, update_string, a function that defines a string, prints it, and then updates the string, and then prints it again. Let's look at how would memory management happen in all 3 of these use cases. All right. The function, if you look at it, calls 3 functions one by one. So the main function first calls stack_fn, which defines and allocates space for 3 numbers. Then it calls heap_fn, which defines 2 strings and creates a combined string with it, and finally prints it. And lastly, update_string, which first defines a mutable string. As you can see, it says mut over here, and then pushes something extra to it and then prints it after the update. Let's look at what might happen when this actually gets called. Let me quickly run this in Visual Studio Code once, just to show you what exactly happens when this code is run. You will see stack function, the sum of this thing, and this thing is 30, and then the heap function followed by before update and then after update. So all 3 of these functions are getting called. This function logs the very first line, heap function logs the second line, and the last update string function logs these 2 lines. This is how the function executes. But how does the stack look like during this time? How does the heap look like? Let's try to figure that out together. Let me open this code on the left, and let me open Acceledraw here on the right. If this is the RAM divided into 2 parts, stack and the heap, the very first thing that gets pushed onto the stack is the main function frame, which defines no functions, no variables. So there is no need for any extra space here. You don't need to push an i32 number here. If I did define, let a equal to 1 here, then sure, I would have had to push or store 32 bits here. But since there is no function, no variable defined here, this stack frame can pretty much be empty for the main function. Then the first function gets called, which is the stack_fn function. And what does this do? It defines 3 variables, which means we need to store 3 variables, each of 32 bits here in the second stack frame. The heap is still empty as this function executes. It prints them on the screen, and then this stack can be popped off because the function execution sort of ends, and you can move on to the next function called heap_fn. Then this function gets pushed onto the stack. And then here, if you look at it, we have defined 2 strings, and then a third string is created from both of them, which means first, this one will be a little bigger. First, the first string is defined, which means we store some space here, which has again the length, the capacity, and the pointer to the actual string on the heap. So when the first string is defined, this is what it looks like. And what is stored? HELLO is what's stored on the heap over here, which is just 5 contiguous elements in memory. That's the heap. Then we define another variable called s2. So pretty much does the same thing. One thing is defined here on the stack, and then the second thing is defined here on the heap, which is a pointer to WORLND. And then lastly, the combined string is also defined. Sure, it is created using the first 2, but it is still a new string, which means we need a third variable here on the stack, which will be very similar to the ones above. And we'll have a link, capacity, and pointer. And where will this point? Do you think this will point here, considering it has combined both the strings? No. We create a third string whenever you do a format, whatever is done here. Format, macro, add 2 things. This doesn't point to any other existing string. It creates a new string, which is why a third, much bigger pointer will be created here. Space will be reserved in heap for a new word, which is both hello, space, and then you get the idea, WORLD. So this is what the stack and the heap would look like when the second function is called and it's executing. While the second function is executing, there is the main stack frame, and then there is a heap function stack frame. All 3 of these variables pointing to 3 separate spaces on the heap. But never does the heap get updated. Never do you increase the size of the string or decrease it. That's the most interesting bit, right? This is just, doesn't matter. You have 3 strings, could have had 1 string. Remains the same. Nothing complicated here. The slightly complicated bit comes when you update a string. So let's see what happens when the second function stops executing, which means all of this can go out of memory. Rust can clean up all of these resources. How does the cleanup happen? We will come to when we reach ownership. But Rust can be like, okay, all of these are not needed. I'm going to remove all of these. All of this memory gets freed. And then lastly, the third function gets put on the heap, which is update_string. And what does this function need to do? This function will first define a mutable string, which is stored the same way as any mutable string. So like nothing changes there. Length, and then the capacity, and then the pointer to something in heap, which currently stores what? It stores initial string over here. But then we push something to it and some additional text. What do you think will happen when we do this? Do you think this will change at all? The pointer will change, the length will change, the capacity will change. How does the thing on the stack change? How does the thing on the heap change when I update a string? Harkirat, one thing is for sure. Okay, chalo, the heap wali thing to will change. Whatever extra things you have added, which includes, and some additional text. Harkirat, first thing first, heap will change, something extra will get added here. This will be a very long string. But does the length change? It should. If the length of the thing on the heap has changed, then of course the length variable here, which is just a i32, i64, some 32-bit or 64-bit number here, this should also change, right? Because this is eventually used as you iterate over a string, as you print a string, to find where is this in memory and how long should we iterate. This length variable is used. We'll be logging this very soon. So if you don't understand this, you'll understand it a little better when we log all three of these. But do you understand? If you've mutated the string along with the heap data, length, capacity, they will also change. You will increase the capacity of the string. You will increase the length. Harkirat, what is the need of a capacity if you have length? Capacity tells you, I have reserved something extra already. You gave me this much text only, but I reserved some extra space. So if something small gets pushed, just push it here, increase the length. But if something very big gets pushed, what if someone pushes something to the string that is more than the current capacity? Then we need to increase the capacity as well. So that is how the heap would change. The actual length of this thing that's allocated would change. And the length, capacity, and pointer variables here would change as you update the string and then finally push it. Of course, when again this function exits and the control reaches the next line, then sure, this stack from would also get deleted and all of this memory would be deallocated. But how does the length, capacity change? Can we somehow print this on screen and see here? Does the pointer change at all? If I had initially pointed it to something here that had initial string, can I just add more things here and keep the pointer same? Or do I need to move this whole string somewhere else? Because, it might happen that jahan pe I had originally kept it, the place where I had originally kept it does not have enough space. Some other program is using, Google Chrome is using the space right afterwards. And hence you might have to move this pointer as well. It's not necessary. Okay, if you update a string, so you will have the same pointer. You might have to allocate it someplace else because you might not have access to contiguous memory because a different process is using the memory right afterwards. Let's print the capacity, length, and the pointer. Whenever you're printing a pointer, you have to type :p over here. Why, Harkirat, what is this? Why is this different? We'll come to when we reach the println macro. Whenever we reach macros, we'll understand. Well, we will not go through how the println macro is implemented. But there are various types of things that this macro can expect as inputs. And if you're giving it a pointer, you can write :p over here. If you're giving it debug data, you can write :d over here. But we'll get to it when we get to it. Capacity, length, and as_pointer. These three things will log the things that I'm showing here. The length, capacity, and pointer, the three things that are stored on the stack, can actually be logged on any string. So if I print this once first and then once later on when we add some additional data on top, let's see what all changes. Does the capacity change? Does the length change? Does the actual pointer over to the heap, the address of this specific first byte, change as well? Capacity 14, length 14, pointer is OX1306A40. So the pointer did not change, the capacity did change, and the length did change. Notice the length and the capacity are the same. It is only allocating as much space in the capacity as needed by the string. Let's update this even further. Let's keep pushing, more and more data here. And let's see what happens. Does the pointer ever change? Does the capacity ever become bigger than the length? First of all, the very first pointer and the very last pointer are exactly the same. So the pointer never changed. Let's put this inside a for loop. Let's do this a lot of times and see if ever the pointer changes. Basically, I'm trying to change the pointer somehow. There we go. So that we can see this in action, that the pointer does change in case, there is some other process that's using contiguous data right after. Let's try that. The pointer, as you can see, changed at this point. At this point, the capacity was 624, which is, as you can see, more than the length. If the length was 614, the capacity was 624, and the pointer was this. It probably could not have more than 624 capacity. It probably just had, 624 bits, after which something else started. Let's see when it became 624. It became 624 at this point. When the length was 314, they said, bro, let's increase the capacity to 624. The length was, 314. They said, let's double the capacity. Let's have a lot of space reserved, because seems like this string is being updated a lot. But it could only update until 614 bits or bytes. After that, it was like, no, sorry, someone else has taken space after that. If the length becomes even more than this, which happened at this point, it was 614 and then it became 639. It said, sorry, we need to move the pointer away. So if you look at it, the pointer was at OX141F04080, got moved to OX412, basically means, someplace else, because the capacity had to be increased, and it cannot be increased. It cannot be increased here because there is a program right under it that's using the memory that comes right after. So it first got moved here to the left, and then some more space got added here, and the capacity became, whatever, 1248. So a lot of capacity got added. And this can happen again. Something else might be sitting here, so you might have to move it somewhere else. So, you ask the operating system for a fresh place to put your data in case it runs out of, contiguous memory. So that is how, the pointer changed here. And then, this one was good enough. It kept on continuing until the capacity became very big. The length became very big. Notice, after a while, the Rust process itself allocates a lot of memory. If it feels like, Chani, this string is getting appended a lot, let me increase a lot of capacity so that I don't have to keep changing the pointer or keep asking the capacity to be increased. That is how the third update string function sort of updates the string, which is the most, I would say not most time consuming thing, right? Asking the heap to, allocate a new space, asking the heap, yeah, please put this data here, please put this data here, please get this data from here, so on and so forth, is slow. Stack is much faster. If you just want to get the length, it's fine. Just want to get the capacity, it's fine. Just want to get the pointer, it is also fine. But if you want to actually print the string, iterate over all of these bytes, that is slow. If you ever want to increase the length or the capacity, if you ever want to move this pointer from here to someplace else, that is very slow. That is exactly what happens here when you keep pushing to the string again and again for a really long time. That is how memory management is done in Rust. C++ is very similar. If you've done C++, there is a concept of stacks and heaps there as well, which is very similar. So there's nothing new here if you've actually done C++. What's new is what's coming up next in the next section, where we understand about ownership, and then in the next section where we understand about borrowing and references. These are the two difficult bits. I'm assuming, okay, stack versus heap is straightforward by now. This is where you store all the fixed time data at compile time. This is where you store all the things that can change in size at runtime. Primary example being strings. As strings change more and more, you might have stored a string over here initially, but you might have to move it someplace else because the string became really long and you don't have enough capacity here at this point to store more data contiguously, which is why you might have to move it a different place. With that context, hopefully we understand stacks and heaps. Let's move on to ownership in Rust, which makes it extremely memory safe, which tells it when to drop variables, when to deallocate memory. Why do you not have to do manual deallocation of memory in Rust, very similar to C? How does it do it itself? How does it know, okay, this is the right time for me to deallocate data? All right, I've made the slides a little more fancy for this one and have some real world examples which are a little problematic, but I'm going to run with them. These examples might help you understand ownership a little better, but this is probably one of those concepts that will take some time for it to, cement in your head. There's a very nice reference of pretty much all the things that we're covering, but if you want to specifically learn about ownership, the Rust book has some great examples. A lot of them I've sort of used here as well. So feel free to look at this. If you want to learn about the stack and the heap as well, there's a decentish explanation here. But specifically ownership and all the examples that they give here are pretty solid. A lot of them I'm using here as well. What is ownership to begin with? Ownership is a set of rules that govern how a Rust program manages memory. The biggest, moat of Rust was what? It is memory safe. Hence, it needs to provide you with the rules, with constructs to do memory management. Ownership is one such construct. All programs have to manage the way they use a computer's memory while running. Be it a C program, be it a JavaScript program, be it a Rust program. They all need to manage the computer's memory. Some languages have garbage collectors like JavaScript that regularly look for no longer used memory as the program runs and deallocates it. In other languages, the programmer must explicitly allocate the memory and deallocate the memory. What is this language? C. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. Rust says, okay, I will make your life really hard when you're writing code, but I will do memory management for you. As long as you follow some rules of ownership, I can guarantee you there will not be any dangling pointers, which is very common in C. There will not be any double free errors, which are not as common in C but happen from time to time. You follow some rules, and if you have followed those rules, I will compile your program. If not, the program won't compile. This is why people say it's very hard to get the program to compile. But when it compiles, it will be very safe and it will most probably do what it's supposed to do. None of these features of ownership will slow down your program while it's running. They will make it slow during compilation. This is why another downside of Rust is that compilation can take a lot of time. Sometimes the program can take 50 seconds, 60 seconds to compile, because the Rust compiler does a bunch of these ownership checks and makes sure you have followed these rules. If you have followed these rules, Rust is like, you leave memory management to me. I will manage all of your memory over here. And by memory here, we mean the heap memory, not the stack. Stack is like fairly easy. There's no complications there. Most complications happen, most null pointer errors, most dangling pointers happen on the heap. So all of these things that we'll talk about throughout this slide, and ownership as a concept makes more sense for memory on the heap. Memory on the stack, you can conceptually think of ownership there, but realistically, ownership is meant for things that are stored on the heap, things like strings. With that definition out of the way, let me quickly introduce you to Rihanna, very similar to one of my exes. She always wants to keep a boyfriend. So she can never be single. That is her rule. Okay, bhai? Ever since I was born, I was 0 years old, maybe not that, but you get the idea. She will have a boyfriend. And I'm equating boyfriend to an owner here, which is what I feel will get me cancelled very soon. But bear with me for a second. What does she say? She says, I always want a boyfriend. She's also very desperate. She's like, I want one boyfriend, but only one, and can never remain single. She says, if I ever remain single, I will die. So she's of this opinion, that as soon as I will be alive, I will need a boyfriend. She can also only have a single boyfriend at a time. So she's like, I'm happy changing boyfriends, but I will have at least one at a time. And if all of them leave me, or all of them die, or the last person that I was with dies, then I will die with them. I do not want to live unless while my boyfriend is dying, he passes me on to the next boyfriend, or I find another boyfriend right the next second. If not, then I will die with them. That is what Rihanna does. Hoping this doesn't cancel my channel. It probably will. But I think this is a great example to understand ownership. I'm going to get cancelled really bad. Stack variables. So firstly, as I said, ownership does not make a lot of sense for variables that are stored on the stack. That includes things like numbers. But if you want to conceptually think of them, feel free to think of ownership from time to time here. Let me take you through a few examples and let's understand how memory management happens here. There is no heap memory management that will happen in any of these examples. So simple stack variables that are created. Let x equal to 1. We initialize a number. Y equal to 3. We initialize a number. We say, I'm going to call println, which calls the sum function and passes x and y. I have a question for you here. What do you think this x and y is? Do you think it is passed in by reference, which basically means, do you think two new variables a and b are created here? Or do you think these variables are only put over here? New variables aren't created. Let's go to AcceleraDraw. And if you remember, how was the stack created? Ignore the heap for now. Let's say this is the stack. We first created the stack frame for, let's say, a main function where we have defined oopsie daisy, where we have defined two variables x and y. So x will take 32 bits, y will take 32 bits. Then this calls the sum function, which means we will push another stack frame here. And now if you remember, we would create new variables, right? A is a new variable, 32 bits. B is a new variable, 32 bits. We copy over the contents, especially for things that are stored on the stack. The things for which you know the size is known at compile time, you don't pass them in by reference. It's not like these values are getting moved here. There is an original xy variable. There are two more variables a and b created. There is not a lot of overhead to create these. So when this function gets called, a and b are two variables here. And then we define the third variable called c, which will also be, of course, 32 bits, which is just the sum of a and b, and then we return it. Cool. So nothing too out of the ordinary to do here. Whenever some function exits, of course, this goes out of scope. This gets popped off the stack. Another variable, if I did a const c equal to sum over here, another c variable would have been stored here. Whenever the final main function ends, this also gets popped off the stack. So as you can see, memory management isn't anything difficult. There is no need of ownership over here. Very similar to what you would expect. C, A and B are defined here. Whenever this function stops executing, they will go out of scope. This might sound trivial since the function is popped off the stack, all variables go away with it. And this is something we've seen from time to time. Here is another example, which is also not too difficult. Here you can also define scopes like this. Here there is a variable here, again a stack variable. And then I define another variable, but inside some scope. And then whenever this scope ends, the function sort of ends with it. Or sorry, the variable also gets popped off. It does not remain in the stack anymore. It's not valid over here. You cannot use it, which might also sound very obvious. Harkirat, of course, this is described between these scopes. So I can't really use this outside because it won't remain valid outside this. And the same is true in JavaScript as well, right? If I do something like this, let x equal to 1, and then try to do a console.log x. X is not defined because x was defined in this scope. You can't really use it outside, even though it's a simple variable. It's a simple primitive stored on the stack whose size is known at compile time. You cannot use it outside the scope in which it is defined, and you can define multiple scopes inside the same function. This has nothing to do with ownership, neither this nor this. These are just examples of slowly getting there. This is how memory management was done for stack variables. Let's get to some heap variables. Yeah, heap variables are like Rihanna. Remember Rihanna? What are her conditions? Ever since I get born, I will have a single boyfriend, and a single boyfriend can pass me over to another boyfriend. Or if my last boyfriend dies, then I die with him. Either they pass me on to someone else or I die. There is no third option. Heap variables are like Rihanna. They always want to have a single owner, and if their owner goes out of scope, they get deallocated. Heap variables say, one of the problems with C that Rust tries to solve is memory management. Memory management specifically on the heap only. Stack is fine. Memory management on the heap is the most error-prone thing in C. This leads to dangling pointers. This leads to something called the double free errors. This leads to a lot of very commonly known errors in C. And Rust aims to solve it. Rust is like, I want to solve these errors. I want to make sure that every Rust program is memory safe. Even if the developer wants, they cannot run into dangling pointers or double free errors. What is dangling pointer? As the name suggests, you might have something in the stack that points to a value in the heap that is no longer valid. You ended up clearing this value by doing, whatever, malloc, alloc, whatever are the ways to allocate and deallocate memory in C, and you still have a pointer to it. So this is now pointing to invalid data. This data now might be some Google Chrome data that I'm running over here, right? My Google Chrome is also storing some variables in heap, and I am trying to access that versus, trying to access my own program data because I have a dangling pointer, a pointer that is pointing to something that doesn't even exist anymore. What is a double free error? Yeah, there was the first variable of mine that tried to free this memory. I tried to call, malloc, alloc, whatever is that function to deallocate memory. And then Google Chrome put some data here. The computer thought this has been deallocated. So Google Chrome put some data over here, and then I ended up freeing the same thing again. So that is another very big erroneous thing, right? You don't want a C program to be able to delete memory or free memory that is owned by Google Chrome. How do you fix these? How does Rust fix these? Rust says, anytime you put something on the heap, there will be some variable on the stack that will own it. I repeat, Rust says, yeah, you create as many heap variables you want, but every variable that you create will have an owner over here. Harkirat, that sounds straightforward. Whenever you create a string, sure, you have a pointer over here. You are saying this, if I do let s1 equal to string : from h, then h will be stored here or whatever. Let's say hello, just to make it a little more cleaner. HELLO. So you're saying basically this, right? Harkirat, you have 5 bytes here, HELLO. And then you have the s1 variable here on a stack frame, and this pointer is over here. So Harkirat, you are saying s1 is the owner of this data on the heap. Yes, I am saying that s1 is the owner of this thing. You can, whenever you define a heap variable like this, you will say s1, which is on the stack, owns this thing on the heap. And what did I say? This thing on the heap is like Rihanna. It cannot live if its boyfriend dies. So if s1 ever goes out of scope, if the stack frame gets popped, the heap deallocate itself. It's like, okay, I'm going to die. My boyfriend died. That is the first thing. Might sound obvious to you. Why did you have to introduce ownership? ये तो मुझे पता ही था. I तो knew this only. If the variable dies, probably the heap will get cleared. So what is new here? I will tell you what is new. The new thing is, if you ever try to do this, let s1 equal to this, and then let s2 equal to s1. If you ever try to do this, s2 is not a copy of s1. This code that I've written here, the 2 lines of code, first line will create this. It will have a variable on the stack, which will point to something on the heap. Second line will not do this. It will not do, let me copy over everything. Let me create another heap data here called hello. And the s2 variable is going to point to this second one. It will not do this. This is very expensive. If you try to do let s2 equal to s1 and it copies over the whole thing, creating something in the heap is very expensive. So you don't want that. So what will it do? It will create the s2 variable. And it will say, s2, you also point here. S2, you also point to the same hello variable or same hello pointer. But here is where the problem arises. This is the source of problems like dangling pointers and double free errors. Here, 2 people are owning this. If one person dies, it will probably try to clear this. Here, I am dying. I am going to kill you as well, or I am going to clear the data over here while another person is active. This is similar to Rihanna having 2 boyfriends. Rihanna is like, if this guy dies, and if this guy dies, this guy will be like, no, you die with me. That is what you promised. If I die, you will die. And then the other guy is like, where did Rihanna go? I thought Rihanna should be alive. So Rihanna says, I want to avoid this always. I will only have a single boyfriend. If you ever try to do let s2 equal to s1, then sure, s2 will become my boyfriend, but s1 is no longer my boyfriend. S1 is no longer valid. I will say I have moved from s1 to s2. S1, please kill yourself. You are no longer valid because I have moved on, or I have moved over to s2. This is how ownership works in Rust. Rust says, anything that's on the heap will have an owner. And if you ever try to change the owner, then the original owner will become invalid. What does becoming invalid means? It means you cannot use s1 anymore. It will begin to complain. Let's write this code. Let's see it in action. But before that, this is what it looks like diagrammatically. Okay, first let s1 equal to some variable was stored on the stack and pointing to the heap. And whenever you did let s2 equal to s1, this no longer remains valid. And s2 is the new boyfriend of this data on the heap, or s2 is the thing that owns this data on the heap. Why does Rust emphasize so much on this? You cannot have two boyfriends or two owners, because Rust says, yeah, this has been historically the thing that leads to most of the dangling pointer errors or double free errors. Okay, bhai, the same thing is being owned by two things, and then one of them will try to remove it, other one will still have a pointer to it. That's what a dangling pointer is, right? Okay, I S2 said, excuse me, S2 said, okay, I want to clear you because I am dying, but S1 still has a dangling pointer to it. It's dangling because this thing is no longer valid. And what does double free error means? Okay, both of them. First, this guy tries to clear it. The computer thinks this area is clean. It gives Google Chrome this memory. And then this guy also tries to clear it. Okay, sorry, I thought my hello was here, my wife was here, but wife has already died. So that is why Rust just clearly says, yeah, this is not allowed only. I want to avoid this at all costs. No conflicts. Anything on the heap will have a single owner. If someone else tries to access it, S3 equal to S2, then S3 will become the new owner of it, and S2 will die. S2 is no longer valid. Now, what does no longer valid mean? Let's try to code it and understand. But I hope this diagram is sort of clear. Okay, if I introduce an S3, S3 will point here and S2 will become invalid. Let's try to see how that happens. Let's define a function main where I create the first string S1 equal to string from hi there, and then let S2 equal to S1. Let me try to print S1 after this. And what does it say? It says borrow of moved value S1. It says S1 has already moved, bro. S1 is no longer valid. She has moved on with S2. And that means that you cannot use S1 anymore. S1 is dead. If you try to use it, I will not compile your program. That's what I meant when I said Kit asks you to follow some ownership rules. If you don't follow them, program won't compile. If I try to compile this program, what does it say? It gives me a hint over here, which we will ignore for now. But it says, bro, borrow of a moved value S1. S1 has already moved. This is no longer valid. I am sorry, but you cannot use S1 anymore. And why is this done? So that two people cannot point to the same thing to avoid memory issues that will eventually, inevitably at some point come. So Rust prevents you right here. Okay, now the owner of this data on the heap is S2. You use S2 as much as you want. I'm sorry, you cannot use S1. It is defined here. That is fine. But beyond this point, S1 cannot be used. Can it be used before this point? Yes. You can print it before that point. But after that point, no longer valid. Great, Harkirat. I sort of understand. This program will now run. And as I can print S1 before moving it. The girlfriend can have fun before she moves on. But once she moves on, this guy dies. So this guy cannot do anything. He cannot, be used at all. He's dead. S2 can. That's the new boyfriend having fun. Why does this become so useful? Why does ownership become so useful? Because Rust says, care for these heap variables. Whenever the owner goes out of scope, I will free the memory. Rust says, care, memory management is very hard. When should I remove this? When should I tell the operating system that this area is clean? You can give it to Google Chrome. It says whenever the current owner of this data dies, I will clear it. So what does that mean here? Whenever S2 goes out of scope, which is, after the main function dies, the heap data gets cleared. Memory management has been offloaded to Rust. You don't have to manually call malloc or alloc, or you don't need a garbage collector to know that S2 will go out of scope here. So let me garbage collect and free this memory. Rust says, as this is my rule, okay, whenever a variable goes out of scope, whatever it was owning, that data also goes out of scope. This is what makes Rust extremely memory safe. Rust says, jo bhi ye problematic data hai na, all this data that leads to these errors, I'm going to be very strict around it. Okay, you will need to have an owner. And when your owner dies, I will kill you. No third way to clear this data. This is the only way to clear data on the heap. So that's what ownership means, I'm hoping it's straightforward now. Okay, anything on the heap will have an owner, and it can only have a single owner at a time. And whenever this owner goes out of scope, this data gets cleared, which basically means if I have another function here called, create underscore str, which defined this, which had all of this logic basically, then this string will be created in this function and then eventually get cleared over here. If I call create underscore str here and then do, whatever, print a random number here, S1 will get defined here. So which basically means this will get defined over here. Then S2 will take over S1 as the owner. S1 will become invalid. Then it will get printed and go out of scope. When the control reaches here, S2 has gone out of scope, which means I will clear the data on the heap as well. That is a rule of Rust. Okay, whenever your owner goes out of scope, this data gets cleared. Another example of this is where it gets a little complicated. When you move on, sometimes, you tell your original boyfriend, sorry, I'm moving on, let S2 equal to S1. Sometimes you are a little shady about it. Sometimes you don't tell them directly. You move on in a very random fashion. You don't tell them. You go on a trip and then the original boyfriend finds out, oh shit, she moved on. So that is another way for you to move a value, which is this. Now this will be complicated, so let's try to read through it. What does it say? It says the string my underscore string is defined here. So who is the owner of this? Who is the boyfriend of this data on the heap? It is this variable right here. But she cheats by going into a function called take ownerships. As soon as what happens when you pass in a variable? Harkirat, when you were passing the variable that was a number, then you told me kid gets copied. So if this was a number, and if this was, whatever, I32 here, I told you, okay, this will remain on the stack here in the main function, and this will remain on the stack here. The other function whenever this gets pushed, there are two variables basically. This will be the first variable. If you look at this code, and let me put this on the left and let me open Accelerator on the right. What happens here? First, the main function will have the first number over here, which is, it's called my underscore string, but you get the idea. It's 32-bit. Then takes ownership gets called. So this gets pushed on the stack. And here, sum underscore string is another 32-bit variable. We have 64 bits here on the stack. That is how numbers are transferred when calling a function. But strings are different. If you pass in a string, like I did over here, then you don't copy it over to begin with. You don't have two separate. Firstly, strings are not stored here. They are stored where? They are stored on the stack. So string, if you define a my underscore string, where is it stored? It's stored on the heap. Whatever it is, HELLO. So this first variable points over here. And then you call another function called takes ownership and pass in this variable. So this variable reaches here. Some string now becomes the owner of it. Because you can't really share. You can't be like, you also point there, you either create a copy. You can call .clone over here. And then the error goes away. What does .clone mean? It means that this will clone the string. So we will have two strings. And now it is fine. This can point here. Of course, this is not a number anymore. And this is also not a number anymore. If you clone the string, when you're passing the string called .clone, it's like this woman Rihanna sending her sister to take ownership. Okay, you have a new boyfriend, some underscore string. I am going to remain loyal to my boyfriend, my underscore string. But if you don't clone, if Rihanna goes herself, then she's like, sorry, some string is now my owner. Sorry, my string, you are no longer valid. I have moved on. Even though I did not do something like this, I did not do let some underscore string equal to my underscore string. I did something else. I passed it in a function, but still, what does passing in a function means? It means the function now needs to point to the same data. And what did we learn? Okay, two things cannot point to the same data. You either clone it, but if you don't clone it, if you pass it like this, then the Rust compiler by default does not clone it. Cloning is extremely expensive. So it happens for numbers because numbers are known, their size is known at compile time, they stay on the stack. But if you want to clone on the heap, you have to ask the operating system for more space and then copy over the whole thing over here and then point the second thing over here. So by default, you don't clone. By default, you refer the same place. But what have we learned? Okay, this guy cannot have two owners. So the first owner will have to become invalid, which is exactly what happens here. My string becomes invalid and you cannot use my string anywhere, any place after that. It says borrow of moved value my string. My string has moved already. The bandi has moved on. So you cannot use my string anymore. He dies, right? That was the rule. If your girlfriend moves on, then you die. That is one of the rules of Rihanna. And that's exactly what happens. The girlfriend moved on here. Now it's not very obvious how she moved on. But if you think about it, if anything gets passed to a function, that function now needs to have access to that variable, right? And that variable, we are not cloning. We are not having two copies like this. Okay, how you can clone it. We are like, nay. We will have the same thing. Rust compiler is like, I don't copy so often. Copying is very expensive when it comes to a heap. So I will just move the ownership from here to here. Now this function has the ownership, which means when this stack frame dies, she dies with it. What does that mean? That means now to bhaiya Rihanna ne bhi apna lifespan chota kar liya. Right? Rihanna also decreased her lifespan because she went with a inferior boyfriend who did not live as long. If she would have stayed with my string, she could have been living until this point. But she went with another boyfriend. That boyfriend just printed and its lifespan ended. Some string moves out of scope here, which means whatever values it owns dies, which means, string is no longer valid after that. You cannot use this hello string. It's gone. It got moved here. And then after that got deallocated from the heap. Nothing, you cannot use it here anymore. This is the second this is where things are complicated and if you look at it from first principles, you would expect, what is wrong in this code? This should work. And if you dive directly into a Rust code base, then also you'll be like, what is happening here? It's like very hard for you to understand it. And then, you Google, what should I do here? And then Google tells you, okay, hey, just clone it and you'll be good to go. And then you do this and move on. But again, you shouldn't clone unless, you don't have any other option. You need to do it. But because cloning is creating a copy both on the heap and the stack, you don't want to create copies of something on the heap unless absolutely needed. You might need it. You might need two copies, in which case it's fine. But, if you don't, then unfortunately there's nothing you can do. You have to pass in Rihanna here and she dies with it. Is there a way to fix it? Yes. Can Rihanna come back to my string? Can she move back with her ex? Yes. Let's see how. But before that, do we understand why this code is invalid? Because rather than doing this, rather than getting another boyfriend like this, just telling him, hey, sorry, I've moved on, my underscore string. Rather than getting a new boyfriend like this, she just went into a function, went on a trip, and then just told the boyfriend, sorry, I already moved on with some underscore string. You are no longer my boyfriend, right? Question is, can she ever come back to him? Okay, sorry, I made a mistake. Let me come back to you and, let's try to make this work. And the answer is yes. So that's the best part about, these references. You can actually make it work if you want. How? What is happening? First, this was the boyfriend. Then she moved on with this guy. She can always come back and make this guy invalid. How? Like this. You can return some underscore string from here. Of course, have to have a return value here. And here you can be like, you can make my underscore string mutable, which means its value can change. And then you can be like, hey, my underscore string equal to this. We are getting back together. Sure, you went away for one trip. It's fine. Now please come back to me. And then, we'll stay happily ever after. Until, of course, my string dies. And then, the heap data dies with it. So that is how you can pass ownership and then pass it back to the main function in case, you really need to do this. But what are the other solutions? You can just clone the string, which means you can have two copies of it. Or another thing you can do here is, something called references, which we'll discuss in the next slide. But do we understand without references? How can we do this? How can we pass ownership to a function and then get the data back? You can also be like, nahi, theek hai. I'll move on with the third guy. Let my underscore string underscore 3 equal to this thing. And then, now this is my third banda, my third boyfriend. This was my first boyfriend. Then I moved on with my second boyfriend. And now I'm moving back with my third boyfriend because my second boyfriend was about to die, right? If I would not have moved on with my string 3, I would have died here with him. Sum underscore string goes out of scope here, which means hello would have also died unless this passed it over to the next variable, or the third boyfriend, which can now carry the legacy forward. Do we get it? What did we learn? We learned that Rihanna is a and we learned about ownership rules in Rust. And we learned about ownership rules in Rust. Again, an amazing resource for this, well, not for this, like for everything that we're learning, is the Rust book. So feel free to go through this doc, pretty much covers the same thing and similar examples. Last thing at the end of the slide is, but what if you want to pass some string to the function and you don't want to clone it and you want the ownership returned back to the original function? You can either do this, the first thing that we did, which is return the value from here and take it in a new variable, or you can mark the variable as mutable and then just take it back in the original variable, or you can use references, which is something we will discuss next. Hopefully by now you understand what ownership is. Let's get into borrowing and references next. All right, borrowing and references. We are going to continue down the same example for some weird reason. Probably shouldn't, but I'm going to. Rihanna upgrades. Let's say Rihanna now says, Kiar, I'd like to be borrowed from time to time. You will still remain my owner. You are still my boyfriend. But from time to time, I would like to be borrowed. Just non-casual stuff. I will still have a single owner, but I can still be borrowed by other variables or other people, I guess, temporarily. What rules do you think should apply to her? So Rihanna and the boyfriend committee decided on a bunch of rules. Here are the rules. Rule number 1. She can be borrowed by multiple people at the same time. That is fine. That she's friends with, but does no hanky-panky. So she can be borrowed by multiple people other than the owner, but she's not allowed to do any hanky-panky with them. Just friends. If she does feel like she wants to do some hanky-panky, then she can only have a single borrower. So she can have an owner and she can have a single borrower that she does the hanky-panky with. She cannot simultaneously be with other borrowers, even with no hanky-panky. So doesn't matter. She cannot be like, okay, I'll just have one borrower that I'll, do hanky-panky with, and others I'll be casual with. No. If you want to do hanky-panky, you are allowed a single borrower only other than the owner. So what are the 3 conditions that can happen? Either she is completely loyal. So owner that owns Rihanna, and that's all. Or if she wants to get a little, not too much, have a little bit of fun, she can have an owner and she can have multiple borrowers. So borrower 1, borrower 2, borrower 3, but no hanky-panky, keeping completely casual. Or the third scenario is, okay, she can have a single owner and a single borrower that she's doing hanky-panky with, but no third borrowers. She cannot have a third borrower in this case that, can be either hanky-panky or not possible. If you have a borrower, that's it. You can have only 2 people that you can do hanky-panky with at the same time. No third person. Or if you want to stay casual, okay, stay casual. You can still have an owner. Or the best case, she remains loyal forever. Let's translate these to Rust terms. Owner we understand now. Ownership we understand now. Borrowing is another concept in Rust, which states, here you can borrow a variable if you want the owner to still be retained. What was our problem in the last slide? The problem in the last slide was that we had to do this weird hack to bring back ownership to S1. We said let mutable S1 equal to this. We unfortunately ended up giving the ownership to this guy and then ended up taking back. So this is like very weird code. What if we can pass S1 by reference somehow, which is equivalent to saying, okay, some string has borrowed hello for now, and it will return back eventually. The thing about borrowers is, if borrowers die, Rihanna doesn't have to die. Rihanna still only dies if the owner dies. Borrowers, they can come and go, they can die, they can not die, but Rihanna won't die. She has zero effect with either of these borrowers. But if the owner dies, she still dies. So Rather than passing her to a function and giving some string the ownership, we can say some string please borrow, and then eventually, this function will die and the borrower will go away. So that is what borrowing means here. Let's understand what references are to understand borrowing a little bit better. References mean giving the address of a string rather than the ownership of the string over to a function. For example, let s1 equal to some string and then let s2 equal to at the rate of s1. What does at the rate of s1 mean? It means the address of s1. Basically means something like this. Here s1 has been defined and a new variable s or s2 was defined that points to s1. So the owner is still this. If this guy goes out of scope, this data still dies. But the new variable s that we have introduced just points to it. This guy doesn't own this. This guy has no concept of a length or a capacity. It's just dependent on the main owner. If you look at this code, surprisingly it will compile. If I go to Visual Studio Code, what code would not compile? If I do this, it will give me an error. It will say, hello has been moved to s2. You cannot use s1 anymore. Borrow of moved value s1. But what if rather than changing the owner, s2 just borrows hello for now. Okay, I'm just borrowing it, going to use it. And then s1 is also valid. She was borrowed and not actually moved, which is why this code is still valid. The first pointer wasn't invalidated. S1 is still valid. It just looks something like this. S1 is valid, S is valid, or S2 in this case is valid, and so is the data on the heap. Borrowing. You can transfer ownership of variables to functions by that is something we have done from until now. But by passing a reference to the string, the function take ownership. The ownership of the string remains with the original variable in the main function. This allows you to use myString even after the function call. Even after this function call is made, if I've passed it by reference, which means I've passed at myString here, and the type over here is also at string, then I can do whatever I want with it. I, of course, cannot mutate it. This is not a mutable variable to begin with. We'll get how you can do that later on. But I can use it without grabbing any ownership. If I want to keep it casual, I'll be like, okay, yaar, please come here, let me do my thing, and then my string is still the owner, it's still valid throughout. So if I copy this code and try to run this, you will see it also compiles. If I don't pass at my string here, then of course the original problem comes that the ownership of this goes to this function. But if I pass by reference, if I make take ownership, I should call it borrow variable now, because I'm no longer giving it ownership. I'm saying, bro, here is the address, borrow the variable, do what you want to do with it, and then eventually I will still remain the owner, and then print it over here. That is what borrowing a function means, or borrowing a variable means. What is the other way to borrow it? You can also do something like this. Let s2 equal to address of my underscore string. What if I want to borrow it more than once? I can keep doing this. As I said, the rule said she can have multiple borrowers as long as she's not doing any hanky-panky with them. What does hanky-panky mean? We'll get to eventually. But as you can see, I can have multiple references to it. And each one of them will be valid if I try to print any one of them. S2, S3, S4. The code compiles, it's all good. The reason it's all good is because Rust is like, this is a common use case. If there is a variable which has an owner, a lot of places / variables can refer this. It is fine. There is something else they cannot do, which will come to very soon, but they can all refer the same thing. I understand my rules. I know if my owner goes out of scope, all of these will also become invalid. And if either of these goes out of scope, this doesn't change, this doesn't change, still remains in the heap. As long as the owner is alive, this data still remains in the heap. That's what the memory management rules state in Rust. Right. Next up, let's understand mutable references. If you remember, I said she can only do hanky-panky with one. That is the equivalent of mutable references over here. What if you want to update the value of a variable? Let's say I write this code over here, or just copy this, I guess either is fine, which the function is called update word, and it needs to update the string. So let's say I define a string over here. Let's say we did not have any function. How can you update this string? Number one, You need to make sure it is mutable. If it's not mutable, you will not update. You cannot update it. It's most default variables in Rust are what? They are immutable. So the first thing you have to do is specify that it's mutable. Then you can call s1 dot push underscore str and push whatever string you want after it. Let's say world. And now if I try to print this, you will see the thing that gets printed is hello world, which means I was able to update the string. Now what if I want to define a function called update underscore str, which takes a string as an input and borrows it? I repeat, this guy borrows a string, there's an @ over here, and tries to push something to it. Notice there's an error over here. It says cannot borrow star s as mutable as it is behind a reference. S and @ reference, so the data it refers cannot be borrowed as mutable. It is saying, I get that you're borrowing data, but you're not borrowing the data mutably. Even without calling the function, it knows it. At compile time itself, the Rust borrow checker is like, no, this cannot happen. I'm sorry. You cannot update data unless you do this. You say, I'm going to take a mutable reference. You say, I'm going to borrow and I'm going to do some hanky panky with it. I'll change the shape of this specific variable. Now, if I call update underscore str with @mute s1, it will work. It will of course not work if I pass @s1 here. You have to pass it as a mutable reference, which means I am still borrowing it, but I am borrowing it mutably, and I can update it now that I've borrowed the variable mutably. No red squigglies. If I run it, it still prints hello world, and now the hello world update is happening in this function. This is how you can pass a variable to another function mutably so that the function can actually update it. This might sound straightforward, even though I would urge you to code this yourself locally. Remove the whole thing and try to code it. First define a main function, then create a string called hello. Then write a function update underscore str, which takes what? It takes a string as an input. What is the type? It is @mutable string. What does it return? It doesn't return anything. And what does it do? It does a str dot push underscore string world. And now I can simply call update underscore str. When I'm calling it, I need to pass a mutable reference to str. As you can see, there's a red squiggly here. Why is there a red squiggly here? Can you guess? What am I missing? What am I missing? I cannot pass a mutable reference to str if str itself is not mutable, right? So I need to make sure this is mutable, and now you're good to go. That's how you do mutable references in Rust. This might feel very obvious and like, okay, Harkirat, this sounds simple. But now come the rules that we had discussed initially. The rules that make borrowing also memory safe. Let's see what those rules are. The rules say, I'm ignoring this. You can try it. Let's copy and try what it says. It says, here I'm going to define a variable called s1. And I'm going to mutably borrow it like this. You can also borrow it like this. I repeat, it's not necessary only if you can pass it like this to a function. Can a function mutably borrow it? You can also be like, let s2 equal to @mute s1, which means I'm taking a mutable reference of s1 in s2, and then s2 can just, update push underscore str world, and then I can print s1. So this works. I don't necessarily have to, give it to a function and provide a mutable reference. I can do it here as well. But what does the code do? The code says, you are first going to take one mutable reference and then call update word, which takes another mutable reference. And what did we discuss initially? If she is doing a hanky panky, she can only do it with one person. She cannot have two mutable references. If she has one person she is doing hanky panky with, she cannot have another mutable reference. She cannot do let s3 equal to @mute s1. This throws an error. In fact, she can't even have normal borrowers now. Even if you do a non-mutable borrower, it cannot happen. What does it say? Cannot borrow s1 as immutable because it is also borrowed as mutable. She already has friends, or like has a borrower she's doing hanky panky with. So she cannot have another borrower. That is what the rule stated. What is the rule? If you have one mutable reference, you cannot have any more mutable or immutable references, which is why if I try to call update word over here with at mute s1, it throws an error. The error is cannot borrow s1 as mutable. So what have we learned? We have learned that we can only have a single mutable reference at a time. As you can see, I'm doing let s2 equal to at mute s1 here, which means s2 is now allowed to update the string. I can always do a s2 dot push underscore string whatever. So this s2 has the power to update the string. And if this has a power, you cannot give that power to someone else. You will have the owner, you will have s2, you cannot have a third mutable reference. It will throw an exception that says cannot borrow s1 as mutable more than once. If you have a single mutable reference, neither can you have any more mutable references, nor can you have any more immutable references. If I try to do even this, let s3 equal to at s1, it will still say cannot borrow s1 as immutable because it is also borrowed as mutable. So if there is a mutable reference, that is it. What was the original rule? If she is doing hanky panky with one borrower, she cannot have any more borrowers, irrespective of if these are mutable or not. She's doing it with one, that's it. Cannot have more borrowers. That's a brief about mutable borrowing. Notice a few things here. The rules aren't really enforced unless two conflicting values are used. So like, bear with me for the next 5 minutes. What was the rule? You cannot have multiple mutable references, or if you have a single mutable reference, cannot have another reference. Let me remove this println statement, and you will notice it just compiles. Even though you have a mutable reference here and an immutable reference here, let me try to print the immutable reference as well. It still compiles. It does not throw any error, also runs the code correctly. Why? Because the compiler is smart enough to know, yeah, you did take a mutable reference, but never did you use it. So you never did a s2 dot, update underscore word world. And hence now it will complain. Cannot borrow s1 as immutable because it's already borrowed as mutable. So if you try to use s2 is when it will be like, okay, sorry, a borrow checker rule is being violated. But if you don't use s2, if you print using s2 or don't do anything with s2, the borrower understands that it's fine. Even though you have one mutable reference and one immutable reference, which is not allowed, the code will still compile because it knows that you did not ever use s2. You never ended up using the mutable reference, and hence, using this code, writing this code is fine. Generally though, why does it avoid this specific pattern? Why does these rules apply? If there can be many immutable references at the same time. If I have the string, I can have multiple immutable references. She can have multiple borrowers, Rihanna can. But there can only be a single mutable reference. If she has one borrower that she's doing a hanky panky with, which is this guy right here, this code is not valid. You cannot call update underscore word with another mutable reference. You can only have a single mutable reference at a time. Lastly, if there is a mutable reference, you can't have another immutable reference either. So you cannot have two mutable references at the same time. And also, if you have a single mutable reference, you cannot have another immutable reference either. Why is that? Why is it enforcing these rules on you? Let's understand that. Why does the Rust compiler say, I get that you might need references, but we are strict. You can either do a lot of immutable references, or if you do a single mutable reference, then you can no longer do any more references, be it immutable or mutable. And the answer is, this is to avoid any data races / inconsistent behavior. Again, what is Rust? It's a memory safe language. So it enforces these rules on you when you're writing code, so you don't run into the following errors. If someone makes an immutable reference, they don't expect the value to be changed suddenly. If you had a mutable reference here followed by an immutable reference, S3 would be like, I to made an immutable reference. And if S2 updates the variable, then S3 will is supposed to panic, right? Why? S3 is like, I borrowed it immutably. Why is the value mutating if I borrowed it immutably? to avoid this altogether, you will see this in Rust many times. Okay, there might be a potential of an error somewhere, and it just prevents it upfront by enforcing these rules at compile time. What was the first rule? If there's a mutable reference, no other immutable reference is allowed, because this guy does not expect this S1 variable to change. So sorry, Rust code will not compile. What is another issue you can prevent by enforcing these rules? If more than one mutable reference did happen, there is a possibility of a data race and synchronization issues. If the borrow checker did allow you to borrow it twice mutably, if both of them try to update at the same time, there can be synchronization issues. Harkirat, this though is single threaded, yes, but you can create multiple threads here. So if two threads try to update the same value mutably, then it's a problem. It's a very common attack vector, not attack vector, like common issue you have to worry about as a developer if you're writing this code in C, let's say. So for that reason, it just enforces, okay, you are not allowed to create multiple mutable references. One is good enough. This is what all we allow. Figure out how you can create your application, be it a full stack application, be it a CLI, whatever you're building, figure it out. These are our rules. We enforce them. This is to make it memory safe. Sure, they can be a little strict, but this is how it is. The benefit that you get by making, these strict rules and avoiding multiple mutable references is that you avoid a bunch of memory issues later on. Sure, JavaScript is very easy. In JavaScript, you can simply do let a equal to 1, b equal to 1, c equal to a, and then, c equal to 100. I can mutate c, d equal to a, b equal to 100, so on and so forth. There's no end to how much, everything can mutate everything. This is why I said even JavaScript has a library called Mutable.js, which, lets you create immutables. But, that's the difference between JavaScript and Rust. Rust enforces these rules because it knows over years and in all the problems that comes in C, okay, these are the potential errors that can happen. To avoid them, these are the rules. You have to follow them. Again, the reference. One more thing that sort of is very good to discuss at this point is lifetimes. Because if you've understood this much, lifetimes is another thing that, is 10 times more difficult than what we've learned in this one. And also, something you will see from time to time in Anchor contracts. So you have to learn this if you're thinking of creating Web3 contracts. So two more things. One easy thing to learn is string slices, and one slightly hard thing to run is lifetimes, which I'm just deferring for the next video. But if you want to read about them yourself, slices here, lifetimes you can find somewhere on the Rust book, probably towards the end. So both of them are sort of, available in case you want to read yourself. But I'll probably be creating a second part as well where I'll cover these. Cool. That's all the memory management jargon we had to go through. How was it? Let me know in the comments. As I said, there are still, a bunch of other things. The important ones being these two only, but a bunch of other things that are good to know. Generics, generic lifetimes, 10 different things. I can show you like a very weird Rust code right now that you'll be like, oh, what is happening here? But yeah, we will understand that when we understand a lot of these things. Traits we'll cover a little bit in these examples, and generics, lifetimes, macros, async operations, and a bunch of other things we'll cover here. Now let's do some more implementation. We have a decent grasp on the memory management rules, the borrowing rules, the ownership rules of Rust, hopefully. Now let's do some more coding and understand how do you create objects, how do you create enums, how do you handle errors in Rust. Let's get into it. Alrighty guys, here onwards comes the easy stuff. So shouldn't be too difficult to understand /code. Would generally urge you to code along. But even if not, that's fine. But yeah, you'll forget if you don't code. If this is the first time you're coding in Rust, whatever I'm coding, try to code yourself. Let's kick things off with structs. Structs, I think they exist in C++ as well, if my vague knowledge is correct. But if not, structs let you structure data together. Very similar to objects in JavaScript. What are objects in JavaScript if you've used them? You use them something like this. Let obj or let user equal to name Harkirat, age 21. And then if I do a user.name, it prints the name for me. User.age prints the age for me. If I go back here, what is a struct? Now you cannot create objects directly in Rust. Rust is very type safe. So you first have to define the structure of your whatever you're creating, which in this case is a struct. Struct user active, which is a boolean, username, which is a string, email, which is a string, and sign in count. Let's say how many times this user signed in. This is how you Describe the type of your struct, very similar to types in TypeScript. How do you define types in TypeScript? You write type, user, and then, describe your structure of the user object. Similarly, here we are defining the structure of the user object in Rust. This is the real implementation for it. So this is just the structure. This is the actual implementation. Let user equal to capital user, which means, this struct right here with these properties: active true, username, string.from some username, email, and then sign in count. And then you can print username as you would generally. So let's try to code this ourselves. What's the first thing you have to do? Create a struct user with 4 properties: name, which is a string, and then age, which is, let's say, a string, and then active, which is boolean, and then age should just be u32. Then inside the main function, you can be like, let user equal to user with the name set to Alice, string : from. If this feels weird, you can always define them separately. Let name equal to this thing and use name over here. I think you can also do this. You don't have to provide the value. If the key and the value are the same, you can simply use this shorthand, or you can do this as well. Either is fine. And this will create a struct. Now if you do println dash is dash years old, where the first bracket here represents user.name, second one represents user.age. If I run this, it says Alice is 30 years old. So that's how you create structs. What is the benefit, Harkirat? Why can I not simply do this? Let name equal to something, and let age equal to 30, and then let active equal to true. Why did I have to structure data together? And the answer remains the same as objects in JavaScript. It's a good idea to structure similar data together so you can access it together rather than storing it this way. What will you do if you have an array? Will you create 3 different arrays? One called names, one called ages, and one called actives? No, right? You will have a single array called users, which will be an array of type user struct. So this is generally how you structure data together. Now this gets not really complex. There are a few like weird structs that exist. For example, there's a tuple struct. There's also a unit struct, which are rarely used by say, but good to know, I guess. Tuple struct and unit struct, feel free to Google them. They're probably part of the Rust book as well. They let you define, a lot of times you just need a struct without any attributes attached to it. So, let user equal to user. This is not the best example for it. A good example of this might be, what's a good example of a struct that doesn't need any type? Yeah, I thought a lot. There's no easy example of using a unit struct until we reach implementations. So let's first reach there, and then we'll create a few examples of unit structs. But what are unit structs? Pretty much structs that don't have any attributes associated with them. You might think like, why do you need unit structs, Harkirat, if there's no data associated? And the answer is, a lot of times you might need to create something that doesn't necessarily have a data, but has, some functions associated to it, very similar to a class. You might have a JavaScript class, random, which in the constructor doesn't set any attributes, has 0 attributes over here, yet has some functions, do underscore or do something. And whenever you create an object of the class, you might want to call, a dot do something. So a lot of times you need implementations without any attributes, which is why, we will also be looking at unit structs when we reach implementations. What is implementations? We'll get to very soon. But yeah, without implementations, why do you need structs? You need structs to structure data together, very similar to how we have done here. Cool. With that, let's move to, is there something else here? Oh yeah, can you guess, if you create a struct like this user, is the data stored on the stack? Is the data stored on the heap? And the answer is active true is stored on the stack. It's a boolean. Username, something is stored on the stack, which points to something in the heap. Again, a string, stack on the heap. Sign in count is a number, which means it's stored directly over here. So it's just like defining 4 different variables, right? You've just defined them together. But yeah, where it's stored pretty much remains the same. Side quest, learning about traits. Oh, well, I'm going to leave this here. If you want to read about it or, just go through it, we will be covering this again when we reach traits in part 2 of this bootcamp. So this is part 1. Part 2 will cover traits and how you can derive traits like the copy trait, the clone trait. How are these two different? Why is this copy trait only applicable if you use booleans and numbers, But if you're using a string over here, you cannot use the copy trait, you use the clone trait. Things like these we'll cover when we reach the traits section. But if you want to read through them, I would urge you to, and specifically try to Google/go through the Rust book and understand as to what is clone and what is copy and how are they different and why is this applicable to things that are stored on the stack, why is this applicable to things that are stored on the heap, which is like strings. With that, let's move over to, I think the next thing is enums, implementing structs first, which sort of make structs in Rust very close to classes in JavaScript. You can also implement structs, which means you can attach functions to instances of structs, very similar to classes in TypeScript. If this is a struct that you've defined, you can be like, as you can see, the struct is like, pretty actionable, very similar to the first class example you get in JavaScript or TypeScript. Struct rect has two properties, width and the height, and you can implement a function on it. You can write impl rect function area, which takes at self as an input and returns a u32 or a number. There is no return statement here. That is because you don't need a return statement if the last line doesn't have a semicolon. I can also change this code by copying it locally. So you don't have to write what's written here. You can totally write return self.width as well. Or if the last line is not going to have, a semicolon, if you write just this much, that is equivalent to writing return self.width into self.height. This is a function implementation. Then in the main function, I first create a struct and then I call the area of the rectangle is rect.area. This self variable has access to the width and the height, so it can access all the properties, and you can do whatever you want with it. Very similar to if you would create a class in JavaScript, that will be called rect. Pretty much the same, right? You create a class, create an associated function called method, and then over there you can do a this.width into this.height. Here you can do a self.width into self.height. Self being the first attribute here that's passed by reference, and that's how you do implementation in rect. Another implementation might be function perimeter, which will also take at self as input and return u32. And what will it do? It will return 2 into self.width plus self.height, and you can also print the perimeter of the rectangle, so on and so forth. This will also become useful when we reach traits. When we reach traits, you'll see things like implement debug for rect in case you want to print it in a more prettier fashion. If you want to print the whole rectangle, right now you cannot. If you try to print it, it'll say what does it say? It says rect does not implement the display trait. The trait display is not implemented for rect. So you can actually implement a trait for rect, which should give you a hint of what a trait is. It's like an abstract class, right? It tells you if someone implements this trait, they need to have these functions, which in case of debug is how the thing should be printed. And if you create this fmt function, which prints, you can pretty much print it however you want. The area, the rectangle prints like this. I mean, feel free to ignore if you did not understand this. And if you create the debug trait, this is how you print it. You have to add a colon question mark over here. And if you try to run it, you will see it prints. The area of the rectangle is the rectangle prints like this. So yeah, basically the area of the rectangle is followed by, I shouldn't have had this, but you get the idea. Now I don't have to do a rect.print or rect.log. I can simply do rect because I've implemented the debug trait for rect, which is a struct. But if you don't understand it, it's fine. I covered, implementation. I covered implementation. I also covered traits over here, which is something, you don't have to get into just yet. All right. One last thing that I shared, a while back was, okay, you can have unit structs, which, don't have any attributes. And the question was, what's the use case for that? And, the use case might be here. There is something that we just want to attach implementations to, doesn't need to have any attributes. So, you can be like impl rect and attach whatever function over here called, let's say, area, that you can use to print over here. Of course, this is not a good example here because if it is a rectangle, it should have width and height. But let's say it's something else. It's like a none shape or, a no shape attribute, struct, which pretty much has no shape, and hence the area of it should be 0, which again, you can return 0 here as well, does the same thing. But yeah, this is why you might need a unit struct, which does not have any attributes associated to it. Cool. That's all for structs. Next up, we will be covering Now we'll be covering enums. Yeah, we'll be covering enums, which are almost exactly the same as enums in TypeScript, nothing new. Enums in Rust are similar to enums in TypeScript. They allow you to define a type by enumerating various possible variants. Too much of English here. So let's break it down. What does it say? It says, if you ever have various variants of something or various types of something, use an enum rather than using, constant strings everywhere, which is like the common use case of enums. Just Google enums. They're like language agnostic. And they let you create various or define various variants of something. For example, here it's written enum, direction. Yeah, direction has 4 variants. You can either go north or go east or go south or go west. This is how you define an enum. And how do you use it? You say the main function may let my direction equal to direction : north, which means I want to go into the north direction. And then let new direction equal to my direction nowhere, because copy. Oh, ignore this line for now. I wanted to show something here, the copy trait. Lastly, we call move _ round with the new direction, which is a function that takes capital D direction, which means this enum as an input. And we'll probably implement some logic to move a character around in a multiplayer game. Let's see that in the IDE one more time. Let me remove this line. What does it say? Oh, that's why I need to implement the copy. Or I can just clone. Oh, I cannot clone it. This does not have that. Alrighty, we do need to derive copy over here, which means we need to derive clone as well. Cannot find my, oh, there you go. That's my bad. You probably don't need the trait. That makes sense. Alrighty. This is a cleaner version of the code. What does it say? It says, let my direction equal to direction : north, and then calls a function with that variable. And if you look at the function, this is what it expects at the first argument. You might ask, Harkirat, I don't see any benefit here. First, explain the use case to me. Use case might be you've created a multiplayer game, and this is not a main function. This is some WebSocket handler where you're receiving moves from your end user. You're parsing them and then storing them in this variable, which can be either of one of these 4 values, right? It'll either be north, you either go up in a game, or down, or left, or right. So rather than storing a string over here that says, up, and then having the type of this be string, you can totally do this. You can be like, Harkirat, enums are crazy. You don't need enums. Use this. Yes. But this is a standard question if you're using enums anywhere. Okay, if you have only limited variants of something, 4 variants, up, down, left, right, rather than having literals like these everywhere, which make this function slightly less strict, I can pass some random data here as well, right? Versus if I have an enum with defined types, I can only pass 4 values over here. I can never pass, some random direction. I can never pass something random like a string. Can't even pass, I can have only 4 values. I can either pass north or east or west or south. These are the 4 inputs that I can pass. So it adds more strictness to your code base, given there are only certain variants that you can create. That is what an enum is, and that is why you use it in any language. The syntax to use it here in Rust looks something like this. This is how you define the enum and its variants, and this is how you pass it around in a function. The type of the function that it expects now becomes the name of the variant, or the name of the enum. Why not simply do this? Why not simply pass in a string? Is because, we are now enforcing 4 variants. So this code is much looser than strictly allowing only 4 variants. It makes your code more strict, which is always good. Lastly, this is also something extra that you don't usually see very often, which is a lot of times you might have enums where every variant has some data associated with it. Enums with some values. For example, shape is a great example of an enum. You can only have a few variants of a shape, right? It can be a circle, it can be a rectangle, it can be a square, a bunch of others, but let's say there are just 3. So we say, it is circle, but this circle variant will have some data in it, which is F64, which is a floating point number 64. Similarly, square is a variant which will have floating point 64 as one input, and then rectangle is a variant which will have 2 inputs, not just one, F64 and F64. Now, let's say there's a function. Well, the implementation of this will be much better when we reach the next section of pattern matching. But let's say ignore this function for now. There's a main function. Here you can define let circle equal to shape : circle. But now you also need to give it a value. You cannot simply be like shape : circle, because this variant does expect something over here. Similarly, square has one side and then rectangle has both the sides. So you have to give these as inputs when you're defining the variants. Let's copy this and bring it here. What does it say? One, it defines the enum and also the values associated with it. Two, it has the main function, which, defines three shapes over here with the values. Lastly, it has a calculate area function, which doesn't do anything right now, simply returns 0.00. It returns an F64. You have to, make sure this is an F64. You can do this, or you can do 0.00, doesn't matter. This is probably easier. And you can call calculate underscore area with, whatever shape you want, which in this case, let's say we call it with a circle. Of course, it returns 0 right now, so there's no point printing it, but you get the idea. Okay, circle will take a shape, and every shape has multiple values. Circle is a variant, and it has some data associated, which in this case is just a number. Two numbers that a rectangle needs. Question is, how do you implement it here? Finally, ये तो आपने बना दिया. You made this. This is very easy, very contrived example. Show me how can you calculate area. Will I do something like this? If shape equal to, shape : circle. Something like this, Harkirat. And how will I get the data of the circle if it is that? How will I get this circle radius so that I can return 3.14 into radius Harkirat? That is a great question. There are a few ways. There is a way to do it like this as well. If let shape, something like that. But we are not going to, we can discuss that as well. The better way to do this is something called pattern matching in enums, which is something we'll discuss next. Okay, that's all for this slide. Let's move on to pattern matching. It lets you, as the name suggests, pattern match across various variants of an enum and run some logic. What does the logic look like? Let's look at the calculate area function. What does it say? I'll take a shape as an input and I will match. KR, is this shape of type circle? And if it is, then it has a radius. And I will return, oh wow, that's like one way to get pi, or you can write 3.14 here, into radius. If it is a square, it has one argument over here called side length. Then I will return side length into side length. If it is of type rectangle, then I will return width into height, and it will have two arguments over here. That is what pattern matching lets you do. It lets you match across various variants and calculate a value that you can return from this function. Again, Harkirat, why is there no return statement here? Because if you don't have a semicolon at the end, then adding a return is similar to, just putting the variable over here. Let's try to see that in action. Let's try to write the calculate area function ourselves. Let's create a pattern match. We can do it a few ways. We can also assign it to a variable. Let answer equal to, let's pattern match shape, and it has three variants. It will either be of type shape : circle, which will have radius as the input, and it will return what? It will return 3.14 into radius. Then it can be of type shape : rectangle, which will have width and height, which will return. You can also put this inside curly braces if you need multiple statements. We don't, so like this is fine, but this is also fine. And lastly, the third variant here is going to be shape : square, which will have a single side and return side into side. So as you can see, you can basically the Rust will ensure you have all the variants here. If I try to remove a single variant over here, it will start to complain. Pattern matching expects you to give a value or give a code block for all the variants. If the variant is of this type, do this. If it is of this type, do this. Or if it is of this type, then do side into side. And whatever variant runs, thankfully in this case, all three of them return the same thing, which is a floating number 64, which is the inferred type here as well. And you can simply return this answer over here. And that's pretty much it. That's how the calculate area function can calculate the area. Is there another way? There is another way. If let, is this it? Yeah, this might be it. So yeah, you can totally do this as well, and do pattern matching using if else's. But yeah, this is usually the cleaner and most used approach is to use pattern matching, or you use the match keyword over here. Now let's try to calculate area. Let's try to let area equal to calculate area for the circle, and then let's try to print this. Let's see what it logs. And it logs area of the circle is 78.5, probably is right. And yeah, similarly you can call it for, the other things. In case you want to print something here, println hi there, and then, try to run the same thing with the square, then you will see the control also reaches the hi there block. Sorry, it's on the rectangle. So we have to call it on the rectangle over here. And it says hi there over here, which basically means, the control reached this code block right here, provided the input shape was a rectangle, which it was over here. Cool. That is how you do pattern matching. You will see this very commonly across code bases. Essentially, this is how you pattern match compared to, using if else's. Next up, we're moving on to some common enums, I would assume. Yes, error handling and optional type. These are two common enums that Rust provides you for better error handling, for better null type handling. What does each of these mean? Let's get into next. Alrighty. Next up, we'll understand error handling in Rust. Any programming language that you write will have some flavor of compile time and runtime errors. Let's understand what that means. What are compile time errors? In case you have a language like Rust or C++, you first compile your project into a binary, which means you take the higher order code, the high level code that's written here, which could be, fn main and then some code inside it. You take this and convert this into a binary. This conversion, if there is ever an error here, which could be, the borrow checker complaining, the type checker complaining, or any other issue, which means no binary got spit out from the original code, then that is what's a compilation error. And what is a runtime error? Here the final binary was created, and while this binary was running, something went wrong, something crashed, and the process had to die. But Harkirat, you said Rust is a very memory safe language. So how can there be any runtime errors? If Rust is so safe, it should never error out ever. As long as the code has compiled, it should always for sure run. That isn't necessarily true. There are cases where, there will be a runtime error. We'll see some of these examples very soon. The question is how gracefully you handle these errors. You might have heard of try catch blocks in JavaScript. That's a more graceful way to handle an error. And similarly, Rust provides you a more graceful way to both handle errors and propagate them. Let's understand what those ways are. Different languages have different ways to handle errors. JavaScript, for example, has the concept of try catch blocks. If I write this code where I am reading the contents of a file synchronously and then logging it over here, if this file does not exist, or if this file has some corrupt data, or if this file is already logged by a different file, then this should throw an error. There is no point continuing here because the data variable will have nothing stored. So JavaScript errors out. Now you can either handle that error or you can stop execution right here. Whenever an error is thrown in JavaScript, if you don't put it inside a try catch block, then the execution will stop right there. But if you put it inside a try catch block, then the execution, at least in this scope, would still end over here, which means this line of code never runs. But after this line of code sort of partially runs and the error is thrown, the control reaches the catch block, and then JavaScript can continue to execute. You catch an error whenever a function is throwing one. That is what a try catch block lets you do. Let's quickly see that in action. If I copy over this code and go to either replit or run it locally, you will notice if I try to run it without any example.txt file, the thing that gets logged says error reading the file reference error, fs is not defined, which pretty much means I need to require fs at the top. But that's another, runtime error. As you can see, when the code was running, control reached here and fs did not exist as a variable. This is one error that Rust would definitely catch at compile time. But the read file sync error, the compiler doesn't really know whether or not example.txt exists. It might exist on your machine, it might not exist on your friend's machine. So it can't really stop compilation based on these hard-coded paths. You might be creating a binary for your friend that does have an example.txt. So even in Rust, it will still let you compile your code if example.txt does not exist. And over there, an error will be thrown. Same thing has happened here. It says error while reading the file. No such file or directory exists. Trying to open example.txt. That is how we were able to catch this error. If we did not add a try catch, let's say I put a console.log extra line here with a try catch, this will get logged irrespective of if there is an error thrown here, because from here the control will reach the catch block from where it will reach this line. And as you can see, extra line here does get printed. But if I try the same thing without a try catch error, something like this, it simply throws the error and I don't even see this line of code. Why is that? Because the error was thrown here and there was no block to catch the error. That is where error handling comes into the picture, that there will inevitably be runtime errors. The question is, have you wrapped them correctly in a try catch block? Or the question for Rust is, have you declared a result enum that gets returned from a function that might throw an error? I repeat, the way this is done in Rust is using the result enum. This is an enum that Rust provides you. And if you look at how it's written, it's slightly harder to understand. It says enum result, but then it has something over here and then curly brackets open. It has two variants, one called OK and one called error. But the problem is OK has one value here, but it's called T, which is the same thing that's written here. And error has one value here, which is called E, which is the same thing that's written here. This T and E are what are called generics. If you've gone through generics in TypeScript, this is exactly the same thing. If you haven't, let me give you a quick overview of what are generics in Rust or generally. The problem is this result enum needs to be used for many types of code, and some code might return a string or throw some specific sort of an error. Another code might return a struct and throw some different type of error. If you read a file, it will probably return the contents of the file, which can be a string, or it will throw or return some sort of a stdfs readout error, something like that. So you don't really know what these types can be. You want to create an enum, but you don't know what this first value will be or what this second value will be. When you have cases like these is when you use generics. Let me give a slightly easier example to chew because this has too many things. Let's look at this example right here. As you can see, I've defined a struct called point, and I haven't written that point needs to be either f32 and y needs to be f32, or it needs to be u32 and u32. I say it can be of any type, doesn't matter. As long as the type of x and y are the same, it is fine, we will allow it. And that is exactly why I can create an integer point with x as 5 and y as 5, y as 10, or I can create a float point where x as 1.0, y as 4.2. I cannot have different types for x and y. I cannot do this. Then it will throw an error because I clearly say, both of them need to have type t. Now t can be anything. In fact, t can be a string as well, which is why this isn't the best example. I can write this as well, which is something we shouldn't allow. There's no real point of having strings as, x and y on a point, but you get the idea. This is a generic, which means it can be anything. And if I want here, x can be literally anything and y can also be something else only, totally possible. The only thing I have to do is add another attribute here. Usually the convention is you write t, u, w, x, y, z, but you can pretty much write anything. If you want to write, a comma b here, that is fine as well. As long as it's a capital letter, it means it is a generic, which means any input is allowed over here, any input is allowed over here. X will be of type A and y will be of type B, where A can be anything, B can be anything. If I want to add a third type, let's say z, which needs to be of the same type as y, then I can say both z and y are of the same type B, and x is of a different type, which can be, something else. So the final thing can look something like this. Okay, x is a number, y is a string, and z now has to be a string. If y becomes a string, that means B is interpreted as string, which means z also needs to be a string. If I try to put a number here, it throws an error. But if I convert it into a string, the error goes away. That is how you do generics generally. We will be covering this again in the next video, but this was a quick refresher to understand what? To understand an enum called result. The result enum is not really defined by us. It is something that Rust provides us. It looks something like this. It is written internally in Rust and it looks something like this. It says, here I am an enum and I have two variants, either OK or ERR, error, and they can have either can have any type, doesn't matter, no restrictions. A can be, string number F32, does not matter. B can also be anything, but usually you will notice B is a struct that follows a certain format. Let's look at the examples of a few functions that return a result to you. Most of the times, if there is a function that can error out / stop the thread, it prevents stopping the thread by returning a result with type error. Let's look at one such function. If you want to read a file from your file system in a Rust process, you can use the fs library, specifically the read toString function, given a path, let's say example.txt, returns the content of a file. But as we discussed a while back, there is a high probability that there is no file called example.txt, or this file is logged by another process, which means this process can crash the thread unless it returns a result to you. If you look at the final result that this guy returns, the return type is what? It is a result rather than a string. If this was a string, then yes, you would either get back a string or the thread would crash. But since it's returning a result to us, it is letting us do error catching over here. How can we do error catching? Since we know res is of two types, either it is OK or it is error, we can do pattern matching here, because what is res? Res is just an enum. So if I type match res over here, I can pattern match very similar to how we were pattern matching in the last slide. That hey, if there are some contents, if the result that this function returns to you is OK, then you can get the contents and print them. If it is of type error, which is the second variant over here, then we can print the error. Let me remove this because this is our own implementation. Rust has its own implementation of result. It looks pretty much the same. Pub enum result t, e, OK, t, error, e. Ignore all the attributes that you see over here. But other than that, it's the same struct that we had written over here. Let's try to run this. And it says error, no such file or directory. But as you can see, the thread didn't crash. There was an error in this function, but it returned the error in a very clean fashion. And then you were able to pattern match the error and the control reached here. If there is any code afterwards, then that extra code will still run. The thread did not crash. Versus if let's say I do this, I'm like, hey, function read file from file unsafe, or panic is a better one, I guess, or either is fine. File underscore content, and I don't return a result, I'm like, nahi to yaar, I will either return a string or I will crash the whole thing. Then what can I do? Let res equal to fs read to string, path being example.txt. This will still return to me what? A result. But if I unwrap the result, unwrap basically means, okay, hey, I either want to return the string or I want the thread to crash. If there is an error, I am okay with the thread crashing, it is fine. But I want to return a string over here. I assume example.txt exists, which is a wrong assumption to make. That is what makes this process unsafe. But if you do make that assumption, if the writers of the fs library did not return a result, but returned a string to you directly like I do over here, then the process will crash, because this line specifically, res.unwrap, will take one of two paths. It will either return a string to you, that's what unwrapping means, okay, hey, I want to unwrap from this result, or it will crash the thread. Let's try to call it. And you will notice it says thread main panicked at source/main.rs. If you notice, hi there never got called. So isn't this similar to a try catch block? In the last implementation, we sort of added a try catch block. You're like, okay, this function is sort of unsafe. So here we matched the response. Okay, hey, was it an erroneous response or was it okay? So it's similar to a try catch block, which we completely prevented over here. Here we are okay if this thing crashes, and if it does, we crash the process with it. Which one do you think is better? Of course, it's better if you wrap the thing inside a try catch block, right? Unless you feel like, yeah, my process doesn't need to live only if this specific read from file unsafe, throws an error. So pick and choose, but generally, if you know a function is going to return an error, rather return it in a result than just crashing the thread. Which means if you are writing your own implementation, you can write it something like this. Okay, hey, I'm not going to return a string. I will return a result, which can have the two types over there being string and string. Which means, you can write something like this. Okay, hey, if res is a type okay, then I am going to also return okay of content. But if it has an error, irrespective of what the error is, I am going to return error with the second generic being a string that looks like this, error reading file. If this feels complicated, think of it like this. Okay, I am returning what? I cannot return a string. I have to return an enum. I either have to return okay file underscore contents, or I have to return error. There was an error. That is what this says over here, right? Okay, this function is going to return a result. In what case do I have to return okay? In case this result itself is correct. So basically, I can also do something like this. If let okay content equal to res, then return okay of content, else return error of whatever error message you might want to give. This and not having return and not having a semicolon are the same thing. So this is another way to write it, but pattern matching is usually an easier way to write this. With that, let's move to the other important enum that Rust provides you, which is the option enum. This one right here. Alright, the option enum is an enum that Rust provides you to get rid of null types throughout your code base. In fact, Rust doesn't have a concept of a null type, because I don't know how many of you have heard, but a lot of people claim that having null in code bases was a $1 billion mistake, because you'll face a lot of runtime errors when you expect a variable to be something, but it turns out to be null at runtime. Which is why the option enum was introduced in Rust, and I think very vaguely remember something similar exists in Java as well. The option enum was introduced to handle the concept of nullability in a safe and expressive way. Unlike many programming languages that use a null or similar keyword to express the absence of a value. Rust does not have a null. It says if you ever have a case where something can be either null or a value, you use the options enum, which as you can see is slightly easier to look at than the previous one. What does it say? It says pub enum option. I take in a generic. I will either be of type none, which pretty much means I have no value, I am null, or I will be of type some, which means I have some value of type whatever is the type of the generic that's been passed in. If you ever have a function that should return a null, return an option instead. For example, there's this function called find first a, in which you're taking in a string and you have to return the index of the first a character in there. But what if the string that you're passing in to the function does not have an a character? Right now I'm calling this function find first a with a string called Raman, which does have an a at the first index. But what if I pass a string that does not have an a? A lot of times you might have seen this problem in DSA, where we say कि अच्छा just return a -1 if it does not exist. But usually, in a more safe, having -1 throughout your code bases is a little weird. If you feel like there is no index, you can simply return null. But since Rust doesn't have a concept of a null, you can return an option. What does this mean? Okay, this function returns an option. It might return an index or it might return none. And whoever is using this function, for example, when we call find first string of my string, we have to pattern match to find कि अच्छा, was there some value here? And if there was, then we log something, else we log a is not found. So this is a cleaner way to catch rather than doing if find first a is equal to -1, then print the letter was not found. We return an option and we say, hey, if something was found, then we print that. If not, then we print the letter a is not found in the string. Let's try to look at this code locally. What does the code say? Let me clean this up a bit. Let result equal to as you can see, the return type of find first a is option of i32, which is the same thing that's written over here. And since this is an enum, rest is an enum now, we can pattern match. Okay, hey, was there some value or was there none value that this function returned? And what does the function do? It iterates over all of the characters. This is a slightly more difficult syntax, which we should probably avoid until we reach vectors. Oh, you need the index. Never mind. This is the only syntax you'll have to work with for now, I guess. So feel free to use the enumerate function here as a black box, but eventually we'll understand what this does. We iterate over the incoming string, and if we ever find a character that is a, we return sum of index. Notice we don't return the index. I don't write return index. What do I write? I write sum of index. Also, we add some type assertion here, which feel free to ignore for now. Just because I haven't introduced usize, I've done this. Otherwise, this works as well. But the more important thing here is, if you look at the function, it might look a little weird. Harkirat, why are you returning sum of index? Shouldn't you be just returning index? But what is the return type? It is not usize or whatever i32. The return type is option of usize, which is why if you know there is a value that has been found, you have to return an enum with that value rather than returning the value directly. And similarly, if there is no value, then you return none. That is exactly what this function returns. That's why this function returns an option rather than returning the value directly. So from time to time, you will see this both for the result enum and for the option enum. Okay, at places where you would have just returned a string, you have to return either a sum of a string or OK of a string if you're returning a result, or return none, or return error with some error that a is not found. So this is like the two commonly used enums across code bases to do what? To do nullability as well as error handling in Rust. Are there more enums? Yeah, probably. But these are the most popularly used one. If you ever, if you're using external libraries, which may throw an error. For example, if you use TypeScript ever, if you do axios.post, there is a high probability that this function returns an error. Similarly, whenever you send get or post requests from a Rust process, you will get back a result that you can pattern match on and figure out whether or not there was an error. With that, let's move on to the next section where we'll be discussing about crates, specifically this cargo.toml file, which is very similar to a package.json file in TypeScript. All right, cargo, packages, and external dependencies. Just like Node.js has NPM, which stands for the Node Package Manager, the Rust ecosystem has Cargo. Cargo is a package manager for Rust, which means that you can use it to bring external packages, which are specifically called crates in case of Rust, to our projects. So effectively, you can't really write everything yourself. I mean, you can, but you shouldn't. Just how in the Java ecosystem, there are thousands of libraries, Spring Boot being one of the famous ones. The Node.js ecosystem has a lot of libraries, Express being a famous one. Rust has a lot of libraries that let you do standard things that a developer should offload to, a big library than doing it in-house themselves. HTTP servers being a very popular use case here. The MERN stack has Express, Java has the Spring Boot framework, and similarly, Rust has a framework called ActixWeb, which lets you create extremely fast HTTP servers. Can you create HTTP servers yourself from scratch in Rust? Yes. But should you? Pick and choose, but like most of the times, no. If you're building, simple backends or even complex backends, Actix is like an extremely fast HTTP server. It has benchmarks comparing it to, an Express framework or other HTTP frameworks. So you don't really have to go extremely low level and build an HTTP server from scratch, but you can do that in Rust as well. Generally though, you use other people's packages. For example, if you want to create a random number ever in Rust, you can use the rand crate that you can find over here. This page is very similar to the NPM page for it. It's where it explains what this specific library does. And you can find the documentation of this library over here. For example, here, if I copy this, seems like a little long of a code base. Let's try this one right here. One thing you have to do before you're able to use this code, as you can see, if you use it directly, it says unresolved import rand because we haven't added the rand crate, which you can do by calling cargo add rand. That sounds very sus. But now if you look at it, I can import two things over here. Specifically, the thing that we need to import is the thread_rng function. We also have to import this trait, but feel free to ignore why. Thread_rng, if I call this function, I can store this in a mutable variable. And when I called rng.generate, it generates a random number for me. I did not have to write any logic to do thread safe random number generation. It has already been done over here. I just get it back and can simply use it. And that's what an external library does, right? If I try to run it, you will see I get back a random number. If I try it one more time, I get another one. So pretty straightforward. This is a very simple library. But as I said, you can use libraries like ActixWeb to create full HTTP servers. Cert is another, commonly used library for serializing and deserializing data. If you ever want to, convert structs into JSON, because structs are not simple JSON. Or when you do serialization and deserialization in a smart contract in Solana, is when this library comes extremely useful. Tokyo lets you do asynchronous async await in Rust, but we'll get there when we reach async await or futures in Rust. Request lets you send HTTP requests similar to Axios, and XQLX is a common framework, sometimes known as SQLX, that lets you connect to an SQL database. These are just a few that I've commonly used, but of course there are thousands of crates that you can sort of use from. Another commonly used one would be Chrono. Chrono lets you do date time. This basically means if you want any date time related functions, you can use Chrono. For example, if I want to get the current UTC time, I can import UTC from here, which returns, as you can see again, the concept of a generic here. It returns date time with UTC passed in as the generic. What is date time? It's most probably a struct, and UTC will probably be a struct as well. Yeah, but as you can see, this is a unit struct. Similarly, I can get back local time because I'm not in the UTC time zone. So local colon now will give me my local time, where, you know, as you can see, date time of local is the generic that's passed in right now. If I run cargo run, you will see I get the current time printed in all three of the time zones. So yeah, that's pretty much it. These are simple examples. If when we reach the project section, you know, I'll introduce a few packages that you can use to create whatever you want to create. For example, CLI is a common thing that you might want to create in Rust. CLI stands for command line interface or an HTTP server. But whenever you create these things, you probably are using someone else's work and you don't want to, you know, build it from scratch yourself. And how do you do it? This is the package manager, cargo, and all the crates you can find on crates.io, and, you know, read through the documentations and go from there. Pretty straightforward, and brings us towards the end of this video. There's one thing that I skipped from the whole thing because my throat is killing me right now, which is collections, which we'll cover in the next part, along with traits, generics, lifetimes, multi-threading, macros, and async operations. Here are a few, you know, links to the Rust book in case you want to read it yourself. I would urge you to. One of the best resources, a lot of the examples that I took from here, and the most commonly or like overused examples that you'll find everywhere would be from this book. So yeah, try to read through it. But again, a video will come probably in a week where we'll be going through part 2 of this. Lastly, project ideas. I wish I had a more fancy slide here, but again, my throat is killing me. So let me just share 2 ideas. Considering you know this much, you can try to create a backend for your full stack application. I can tell you it's not very easy, but, you know, you might need async await and Tokyo. So there's a high probability, you know, there's a lot of new things, and you're not able to sort of understand them well. So feel free to pick and choose if you want to do this. CLIs you should be able to create. So maybe try to create a simple CLI that lets a user, I don't know, add 2 numbers. What else can you write in Rust? Yeah, try. So there's one issue in the chest repository to move it to a WebSocket server, but that might also need some level of, what do you call it, async await knowledge. So yeah, pick and choose if you want to do any of these. But again, unless you get your hands dirty, it's sort of very hard to do this. Could have sworn, yeah, migrate the WebSocket server to Rust. Seems like, yeah, there you go. Someone suggested Tokyo Tungsten. What is that? Asynchronous WebSocket for the Tokyo stack. Yeah, so basically you need a bunch of async await, which we have not discussed yet. Feel free to pick and choose if you want to do this. But yeah, those are the 2 ideas that I can think of. With that brings us to the end of part 1. Let me know how the video was. And I'll see you guys in part 2. Bye bye. My throat is dead.